Welcome to the Snoozy Scientist, a warm corner of the universe where science, curiosity, and calm carry you into a gentle sleep. Tonight, we're traveling back more than 2.5 billion years to a time when the Earth was still learning how to live. Back then, the sky above was not blue, it burned with a dim orange haze, thick with methane and dust. The oceans shimmered dark like liquid metal, heavy with iron, and utterly silent. There was no oxygen to breathe, no green upon the land, only rock, water, and the hum of invisible life hidden beneath the waves. For billions of years, life existed only as whispers beneath the water's surface, single-celled, unseen, fragile. And then something extraordinary began. Tiny organisms, fragile beyond sight, began releasing a new kind of gas. To the life that ruled the oceans, it was poison. To everything that would come after, it was breath. This was the beginning of Earth's greatest transformation, a revolution so vast it would sculpt the continents, paint the skies blue, and give rise to every living thing that has ever existed. It happened slowly, painfully slowly, over 2 billion years. This was the Proterozoic Eon, the longest, quietest, and most important chapter in Earth's story. An age when the planet learned to breathe and life began to shape the world that would one day become our own. But what really happened during the age that made life possible? And why did it take billions of years for complexity to awaken? Tonight, we'll step softly into that forgotten world through rust-red seas, frozen continents, and silent revolutions that shaped every breath we take. But before we begin, I would love to know where in the world you're listening from and what the time is there. It is always fascinating to think of these stories being heard across so many different skies. If you enjoy these gentle journeys into Earth's distant past, please do consider leaving a like and subscribing to the channel. A warm thank you as well to those of you who are already subscribed. You're helping this little corner of the internet grow. I hope this story soothes your mind and carries you gently toward rest. Now, take a deep breath and let us step softly into the forgotten dawn that made our world possible. Before the sky ever turned blue, the world was a place of shadow and shimmer. The oceans did not sparkle with the color of life. They were dark and heavy, filled with dissolved iron that stained them a deep, blood-red hue. When sunlight touched their surface, it did not scatter as it does today. It sank into the waters and vanished, swallowed by minerals and haze. Above those alien seas, the air itself was strange. It shimmered with methane, carbon dioxide, and dust from restless volcanoes that breathed without pause. The sky was dim, tinted orange and brown, a restless veil that filtered the light of the young sun. No blue, no clarity, only the soft burn of a planet still finding its balance. There was no oxygen, not a breath that any animal could have survived. No ozone to shield the surface from the sun's radiation. No wind as we know it. No clouds with clean outlines. The air was thick and unstable, every gust tainted with heat and chemicals. It was a time when the atmosphere itself was a barrier to life, not a cradle for it. Yet beneath the surface of those crimson seas, something persisted. In the shallows where sunlight could just reach, tiny cells floated in colonies, feeding on what the planet provided: sulfur, iron, carbon, and the faint energy of the sun. These were the first engineers of existence, simple bacteria that built their lives molecule by molecule. They left no sound, no trace that an eye could see. But they changed the world in quiet ways, breathing out the first whispers of what would one day become air. The land, if it could be called that, was barren. Jagged rocks and silent plains stretched from horizon to horizon. Rivers of molten rock still flowed across some regions, cooling into black glass that cracked and split as the earth shifted beneath it. There were no trees to sway, no soil to hold moisture. The surface baked under the heat of the sun by day, then froze under thin clouds by night. Lightning flickered through the haze, striking oceans rich with minerals and sparking reactions that danced between chemistry and chance. Each flash carried the possibility of creation. Each drop of rain carried elements that would one day find their way into cells and breath. To imagine this world is to see a planet both alive and lifeless at once. Energy moved everywhere, in water, in air, in the trembling crust, but it had not yet learned to sustain complexity. Life existed only where conditions balanced on a thin edge, in the borderlands between light and darkness, warmth and cold, chemistry and chaos. In these shallow seas, bacteria built mats that clung to rocks and sand. Layer by layer, they formed living carpets that trapped sediments and shaped the seabed. Over time, those layers would become the first stromatolites, silent monuments to persistence, to those who might have stood on the shore, had there been anyone to stand. The sea would have seemed still, yet beneath its skin, life was busy rewriting the chemistry of the planet. But it was not yet a world for thriving. Oxygen, though it had begun to appear in the water, could not survive long. It reacted instantly with iron, forming rust that sank to the seafloor. For millions upon millions of years, the ocean itself became a canvas of oxidation, iron turning to stone, stone sinking to silence. It was a slow exchange between the living and the lifeless, a quiet dialogue that would eventually turn deadly for some and miraculous for others. The sun, filtered through the haze, brought warmth but also danger. Without an ozone shield, ultraviolet light struck the surface with ferocity. It would have been a world of contrasts. Dark red seas glowing faintly beneath orange skies, waves breaking against stone, and the faint flicker of microbial life, unseen and undisturbed. Yet, in all its harshness, this was not a hopeless world. It was a waiting one. Every reaction in the water, every breath of a microbe, every shimmer of rust at the bottom of the ocean was a step toward change. The planet did not yet know the meaning of blue, but the chemistry of that color was already in motion. The earth was preparing itself. Beneath the haze and within the oceans, the foundations of transformation were forming slowly and steadily. Iron was binding with oxygen, gases were shifting in composition, and energy was finding new paths to flow through matter. This was the world before air, before protection, before breath, a fragile balance between poison and potential. And though no one could have known it then, this still, crimson planet was standing on the edge of the most profound transformation in its history. For now the seas remained dark, the skies thick, and the life within them humble. But deep beneath those ancient waters, the quiet persistence of bacteria was beginning to tilt the balance of the entire world. The age of red oceans would not last forever. In time, the sky would turn blue, but first, the earth had to learn how to breathe. In the stillness of the ancient seas, something quiet yet monumental began to unfold. Beneath red waters and orange skies, life had been simple for billions of years. Tiny cells drifted in sunlight, feeding on minerals and energy, following patterns that seemed unchanging. But in the shallows where light met water, a new kind of alchemy took hold, one that would rewrite the planet's destiny. These small architects of change were cyanobacteria. They were no larger than a speck of dust, yet within them, chemistry met sunlight in a way the world had never known. Using light to split water, they began releasing a strange, invisible gas. To them, it was a byproduct of survival, an accident of existence. To the rest of the planet, it was the beginning of everything. That gas was oxygen. At first, it made no difference. The oceans absorbed it instantly, the way dry earth drinks rain. Iron, abundant and waiting, reacted with this new breath, binding with it to form rust. The seas began to change color. Layer after layer of reddish minerals sank to the ocean floor, forming what we now call banded iron formations, silent records of that first chemical storm. To the microbes that had known only a world without oxygen, this new gas was deadly. Oxygen, though essential to the complex life of the future, was poison to the creatures of the past. It corroded their cells, disrupted their chemistry, and spread through the oceans like a slow tide of extinction. It was the first global catastrophe, a quiet apocalypse carried by breath. For millions of years, oxygen continued to rise and fall, appearing in waves as microbial communities flourished, then died. Each bloom left behind rust and silence, a rhythm of destruction and renewal. The ocean floors turned to red stone, the skies thinned, and the planet itself began to shift in balance. Above the water, something extraordinary happened. The haze that had once choked the air began to clear. Methane, the gas that had painted the sky orange, reacted with oxygen and disappeared. The world grew colder as the greenhouse veil broke apart. Sunlight reached the surface more directly, but the warmth it brought could no longer stay. The earth began to breathe and shiver. This was no gentle transformation. The planet's temperature dropped. Glaciers crept toward the equator, and vast regions froze for the first time. Yet, even as cold spread and life struggled, the invisible revolution continued. Oxygen filled the atmosphere, slowly forming a shield high above, a fragile layer of ozone that would one day make land habitable. It was a strange balance, death for one world, salvation for another. The very act of living by one form of life had reshaped the conditions for all that would follow. The bacteria that released oxygen did not know what they had done. They were simply surviving, feeding, multiplying. But their collective breath was rewriting the chemistry of the oceans, the air, and the sky. Deep underwater, rust settled in waves. In the quiet of those depths, iron and oxygen met endlessly, painting the seafloor in red and gray stripes that would last for billions of years. Each layer marked a pulse of planetary transformation, a record of struggle and change. What looked like stone was, in truth, the memory of breath. As time passed, oxygen began to accumulate not only in the water, but in the air above. Slowly, the atmosphere transformed from one that suffocated to one that could nurture. The haze thinned further, revealing a world with softer light and deeper color. The sky, once dim and orange, began to shift toward blue. But the cost of that beauty was immense. Most of the early life that had thrived in methane-rich seas could not survive in this new world. Entire lineages vanished. Only a few adapted, finding ways to hide in oxygen-free corners of the planet. Deep mud, volcanic vents, underground pools. It was extinction on a scale never seen before, yet it carried within it the quiet promise of something new. Oxygen, though deadly to many, opened the door to energy. It allowed cells to extract far more power from food, setting the stage for complexity. Every heartbeat, every movement, every spark of thought that would exist in the future depended on that chemistry. In the long calm after the storm, the planet began to settle. The oceans were no longer red, but clearer, more reflective. Sunlight danced on their surfaces, unfiltered for the first time. The air above was still thin, still strange, but it was changing, slowly, steadily, irreversibly. What began as a whisper beneath the waves had become a planetary transformation. The Great Oxygenation Event was not a single moment, but an era, a slow unfurling of change that spanned hundreds of millions of years. It was Earth's first true breath. From this breath came ice and extinction, but also clarity and potential. The planet had been remade, and though it would take eons for life to rise again in new forms, The foundation had been laid. In the stillness that followed, the world exhaled, and the color of the sky began to change. For billions of years, the sky had been cloaked in a dim orange haze, a veil of methane and dust that softened the sunlight and hid the colors we know today. But slowly, quietly, the world began to change. Molecule by molecule, breath by breath, oxygen had gathered in the air. It was invisible, yet its touch reached everywhere. The transformation did not happen in an instant. It took ages upon ages for the planet to clear its lungs. The orange tint began to fade as oxygen met methane, breaking it apart, thinning the atmosphere that had once trapped so much heat. The light that reached the surface grew sharper, purer. The world that had been hazy and muted began to take on form and clarity. And then, at last, the skies turned blue. For the first time, sunlight scattered across a clean atmosphere, bending and diffusing through air rich with oxygen and nitrogen. The color of that scattering was soft, pure, and endless. The sky that had once glowed with a copper hue became a vast ocean of blue, stretching from horizon to horizon. It was a sight no eye had yet seen, but it was the beginning of the world as we recognize it now. Below, the oceans changed too. The waters that had once been heavy and red with dissolved iron began to clear. The endless rusting of the sea had finally run its course. With less iron left to bind the oxygen, the color of the water shifted towards sapphire. Light could now travel deeper, reaching into layers that had once been shrouded in darkness. Life that had lingered near the surface could drift further down, following the sun's glow into new realms. The world brightened, the haze lifted. For the first time, the planet reflected light in blue and white instead of red and brown. Space itself would have looked different then, as if the earth had awakened and opened its eyes. High above, something even more profound was forming. When oxygen met the sun's ultraviolet light, a fragile layer of molecules began to gather, ozone, thin, invisible, and delicate. It became Earth's first shield. It absorbed the harshest rays that once scoured the surface, softening the sunlight and protecting what lived below. It was this quiet partnership between light and air that made the world safe for life to expand. The ozone did not build overnight. It formed slowly, like frost spreading across a window, each molecule adding to the next, but its effect was transformative. The sun, once a source of danger, now became a stable giver of warmth and energy. The surface of the planet responded. Winds shifted as the temperature gradients changed. Clouds began to take new shapes, forming white patterns that drifted across the newborn sky. The rain that fell was clearer, carrying traces of oxygen to the land and the sea, blending the chemistry of the planet into something new. It was a time of stillness and beauty, but also of loss. Many of the ancient microbes that had thrived in the methane-rich world could no longer survive. The oxygen that made the skies blue was their undoing, yet their death made room for what was to come. In their place, new forms of life began to rise, organisms that could not only endure oxygen, but use it. Within the oceans, photosynthetic life continued its work, releasing more oxygen, strengthening the balance. Every sunrise deepened the planet's transformation. Every ripple on the sea reflected the changing light. Imagine the world then, continents still barren, but oceans gleaming with clarity, skies stretching endlessly in blue, and a faint white shimmer of clouds moving gently across them. It was the first glimpse of the Earth we know. The air had become breathable in potential, the light softer, the rhythm of day and night more familiar. The planet, once veiled and uncertain, had found stability. The cycles of water and air began to align. With the ozone above and oxygen below, Earth had, for the first time, the protection and balance it needed to nurture complexity. This was not just a change of color, it was a change of identity. The world that had been hostile and unstable was learning calm. The chemistry of life was no longer only about survival, but about possibility. In the blue of the new sky and the gleam of the oceans, the earth revealed what it could become. It was not yet filled with forests or animals, but the stage had been set. The air carried the potential for breathing. The seas held the nutrients for growth. The light was gentle enough to sustain life, but strong enough to inspire evolution. The great oxygenation event had remade the planet, and now, in its quiet aftermath, the world stood in balance, blue above, blue below, glowing softly beneath the light of the sun. It was the first moment in the long history of Earth that the planet looked alive. The colors we now take for granted, the blue of the sky, the white of the clouds, the shimmer of the sea, all began here in this silent transformation. The haze was gone, the air was clear, and in that clarity, the world took its first peaceful breath beneath an open, endless sky. With the sky now blue and the oceans deep and clear, the earth entered a new rhythm, one of fire, metal, and restless transformation. The planet was no longer cloaked in haze, yet it still burned within. Beneath its calm surface, forces of unimaginable power continued to stir, shaping the crust, the seas, and the air in ways that would ripple through the ages. Volcanoes towered across the young continents, their peaks veined with rivers of molten rock. Each eruption was both destruction and creation. When the lava met the sea, it hissed and shattered, releasing clouds of steam and trails of minerals that drifted through the water like dust in sunlight. These eruptions poured iron, sulfur, and other elements into the ocean, invisible gifts that would feed new kinds of life. The ocean floors near volcanic ridges became strange and vibrant places. Superheated waters seeped from cracks in the crust, rising through chimneys made of metal and stone. These were the first hydrothermal vents, deep sea cauldrons where fire and water met in perfect balance. Around them, the world shimmered with chemistry. The water that poured from these vents was black and filled with dissolved metals. As it met the colder seawater, the metals condensed into clouds of minerals, drifting down like dark snow. Around these plumes, life found a way to flourish in complete darkness. Microbes clung to the chimneys, drawing energy not from sunlight, but from chemical reactions. This was a revolution in how life could survive. No longer bound to the light of day, organisms learned to live from the heat of the planet itself. They fed on the rich chemistry around the vents, sulfur turning into energy, iron passing through cycles of oxidation and reduction, hydrogen bubbling up from deep within the crust. The oceans became laboratories of invention, each vent a miniature world of fire and stone. In these places, the rules of survival changed. Life began to experiment with new metabolisms, new ways to extract energy from the raw elements of the earth. Iron, sulfur, and carbon moved endlessly between rock, water, and living cells. What had once been lifeless minerals now pulsed through the veins of biology. Each volcanic eruption brought new ingredients into this grand experiment. As lava cooled, it released minerals that slowly dissolved into the sea. These minerals altered the chemistry of the water, giving microbes new materials to work with, new reactions to master. The earth itself seemed to be feeding its creatures, teaching them how to use its elements to survive. It was a time when life and planet became inseparable. The crust, the atmosphere, and the biosphere began to communicate in cycles of balance and exchange. Iron rusted, sulfur burned, gases shifted, and through it all, microbes adapted. They evolved to use what the earth offered, creating invisible networks of chemical cooperation. Even far from the volcanoes, the oceans carried traces of this fire-born chemistry. Iron spread across the sea floor, feeding microbes that learned to breathe it in or turn it out. Sulfur drifted in clouds of microscopic reactions, powering entire ecosystems in places where sunlight never reached. From above, the planet might have seemed quiet, but beneath the surface, it was alive with invisible motion, a slow heartbeat of chemistry. The crust itself was restless. Continents drifted and cracked, releasing more gases and heat. Volcanoes rose and collapsed, reshaping the landscape again and again. The air carried faint traces of sulfur and ash, soft reminders of the planet's constant renewal. This was the Earth learning how to recycle itself. Each eruption returned old materials to the surface, and each rainfall washed new ones into the sea. The cycles of metal and fire connected everything: the land, the ocean, and the life between them. The iron that once colored the seas now played a different role. Instead of sinking silently to the ocean floor, it became part of the chemistry that sustained life. Bacteria learned to use it as a catalyst, a bridge between energy and survival. Sulfur, too, became a companion to life, moving in endless loops of oxidation and transformation. In time, these cycles grew stable enough to support entire ecosystems. Microbial mats spread around volcanic regions, weaving networks of living filaments through mineral deposits. The ocean floor glowed faintly with bioluminescence, the quiet light of chemistry at work. Each vent, each volcanic island, each fissure became a node in the planet's expanding web of interaction. The Earth had turned itself into a living chemistry set, its ingredients mixing and reacting in endless variation. Fire built the foundation, water carried the elements, and life stitched them together into something self sustaining. Above, the blue sky watched in silence. Below, the world glowed with energy drawn from both light and darkness. The age of iron and fire was one of quiet innovation, a time when life became more inventive, more resilient, more deeply connected to the planet that made it possible. And in this balance between heat and ocean, between stone and breath, the foundations for everything that would follow were quietly laid. The world was learning patience. It was learning endurance. It was learning how to keep living, even in the shadow of fire. In the quiet shallows of ancient seas, beneath a blue sky still new to the world, life began to build, not in grand gestures or sudden leaps, but in slow, steady patterns that repeated with the rhythm of the tides. Here, sunlight touched the ocean floor, and within that gentle light, tiny architects went to work. They were simple cells, no larger than dust, yet their patience would shape the planet. These were the builders of stromatolites, layered reefs of life, stone, and time. Each one began as a thin film of microbes that clung to the seabed, capturing sunlight and drawing energy from it. As they grew, they trapped grains of sand, bits of sediment, and minerals drifting through the water. Layer upon layer, they built mounds that rose like domes and ridges across the shallow coasts. A living city began to take form, not with walls or towers, but with layers of memory. Each layer told the story of a day, a tide, a pulse of sunlight. Together, they became Earth's first ecosystems, intricate and self-sustaining, both alive and made of stone. From above, these stromatolite reefs would have looked like rippling patterns of color, green, brown, and gold, stretching beneath the waves. When the tide receded, they glistened in the sun, their surfaces slick with living film. When the tide returned, they breathed again, releasing oxygen into the water, a quiet exhale that would one day fill the air. These structures were not rare. They covered coastlines, lagoons, and tidal flats across the planet. The Earth, still young and wild, now bore marks of order and persistence. Each mound of layered stone was a monument to microbial cooperation, a proof that even the smallest forms of life could reshape entire worlds. Stromatolites were engineers before any creature had bones or brains. They transformed their surroundings simply by existing. The oxygen they released helped keep the seas alive and slowly enriched the atmosphere above. The sediments they trapped stabilized the coastlines, creating new habitats for other microbes to join them. They were the architects of habitability itself. Over millions of years, their work continued. With each sunrise, light filtered through clear water, feeding the photosynthetic layers. Beneath them, older generations of microbes lay buried within stone, their remains preserved as fossils of breath and time. To this day, those fossilized stromatolites remain among the oldest traces of life we can find, some more than 3 billion years old, silent archives of the planet's earliest days. If we could stand on one of those ancient shores and listen, there would be no sound, yet everything around us would be alive with motion too slow for the eye to catch. The water would rise and fall, gliding over mats of life that shimmered like oil on stone. Each ripple of sunlight across the surface would feed 1 trillion tiny cells, each one dividing, dying, and layering itself into the reef. For billions of years, stromatolites ruled the world. They were everywhere the sea was shallow and the light could reach. No forests covered the land, no animals swam in the depths, no birds filled the air. Only these quiet colonies, layer upon layer, exhaling the breath that would one day make complex life possible. But dominance in nature is never permanent. The same patience that built them would one day be challenged by the changes they helped create. As oxygen filled the seas, new kinds of organisms began to emerge. Small, mobile, and hungry, microbes that could move began grazing on the stromatolite mats, feeding on their soft upper layers before they could harden into stone. The builders that had shaped the earth for eons now faced competition for the first time. Slowly, their vast cities began to fade. Many reefs crumbled under the weight of time and life itself. New ecosystems rose above them, more dynamic, more diverse, and far more fragile. The age of the stromatolites was ending, but their influence remained. Even now, they have not disappeared entirely. In a few rare places, in the warm shallows of Shark Bay in Western Australia, and in quiet lagoons of the Bahamas and Mexico, living stromatolites still rise from the seabed. They grow just as they once did billions of years ago, one layer at a time, one breath at a time. To see them is to look directly into the memory of the planet. They are the last whispers of an age when life and stone were the same thing, when patience was the engine of creation. Their rounded forms still catch the sunlight, still breathe, still build, and though the world around them has grown louder and more complex, they continue, quietly doing what they have always done, turning light into structure and structure into time. Through them, we glimpse the deep truth of Earth's story, that even the smallest beings, given enough time, can change everything. That creation is not always loud or fast. Sometimes it is gentle, slow, and eternal, carried out one microscopic layer at a time beneath the endless rhythm of the tide. For a long time, the world had basked in the quiet stability that the stromatolite builders helped create. The sky was blue, the oceans alive with light, and the air had begun to fill with oxygen. It was a peaceful age, but peace on Earth is rarely permanent. Slowly, invisibly, the balance began to tilt again. Oxygen, that precious breath of transformation, carried a hidden cost. As it spread through the atmosphere, it began to strip away the gases that had once kept the planet warm. Methane, one of the most powerful greenhouse gases, was the first to fall. The same oxygen that brought life also broke methane apart, molecule by molecule, leaving the planet exposed to the chill of space. The warmth that had long wrapped the Earth began to fade. Sunlight still poured from above, but less and less of it stayed. The oceans cooled, the winds shifted, and snow began to fall where it never had before. The first great chill of our planet's history was beginning. Earth's earliest ice age. It did not happen overnight. It took millions of years for the temperature to slide, like a slow breath exhaled through time. But as the cooling deepened, glaciers began to creep down from the poles. The seas started to freeze at their edges, and white spread outward across the planet. The land, once dark and bare, grew pale beneath layers of frost. The oceans, which had once shimmered blue and green, turned dim and heavy beneath fields of floating ice. Light struggled to reach below the surface. Whole regions of the sea became cold and still. The earth, for the first time, had entered a state of deep slumber. This was the planet's first great climate collapse, a lesson written in snow and silence. Yet even in that frozen stillness, life endured. Beneath the ice, the seas were not dead. In pockets of warmth near volcanic vents, life clung to the edges of survival. There, in the darkness, chemical energy replaced sunlight. Microbes drew power from minerals and heat, building tiny communities that pulsed with slow, steady life. The vents themselves were like hearths in an endless night. Hot water surged upward from cracks in the crust, carrying iron, sulfur, and carbon. Around them, microbial mats formed, glowing faintly in the light of minerals. They fed, divided, and adapted, weaving the chemistry of survival into the frozen world. In other places, thin layers of ice allowed faint light to slip through. Here, photosynthetic life continued its quiet work, producing oxygen even as the world grew colder. Beneath the frozen skin of the ocean, life persisted in stillness, waiting for warmth to return. This balance between death and endurance defined the moment. The world that had once been thriving was now subdued, but not defeated. Life had found its rhythm in extremes, in heat and cold, in darkness and light. It was learning to survive not only in abundance, but in scarcity. The planet itself shimmered from space, bright and pale, wrapped in ice from pole to equator. Some scientists believe it may have looked like a perfect white marble drifting through the blackness of the cosmos. The oceans beneath the ice moved slowly, like breath under a blanket. The atmosphere above was thin and clear, even the winds quieted. But within this stillness, new possibilities were forming. The ice reflected sunlight, keeping the world cold, yet beneath its weight, the volcanoes continued their work. Deep within the crust, fire still flowed. Each eruption released gases, carbon dioxide, sulfur, and steam, that began to gather in the air once again. The planet was not finished with its story. It was only resting. This first great freeze, often called the snowball Earth, was not as absolute as its name suggests. It was more a cycle of deep chill and fragile recovery, a balance between ice and fire that the Earth would revisit many times. But this was the first, and it tested life in ways it never had before. Those who survived became stronger. They learned to live on the edges, in vents and cracks, in darkness and warmth, feeding on the minerals that rose from the deep. The chemistry of survival grew more complex. The patience of evolution stretched farther. Over time, the gases from volcanic eruptions began to rebuild the greenhouse shield. Carbon dioxide thickened the air, slowly trapping heat again. The planet warmed. The ice began to melt. Rivers returned to the land. Oceans broke free of their frozen prisons, and light flooded the world once more. The first great ice age had ended, but its mark remained. It had tested the strength of life and proven that the planet itself could shift between extremes and still recover. It taught the Earth to balance between warmth and cold, between breath and silence. The world would freeze again, many times, but never in quite the same way. Each collapse would carry a lesson forward that even in the deepest cold, something endures. Beneath the frozen seas, beside the volcanic fires, the spark of life had never gone out, and as the ice receded, the earth, tempered by its first great trial, began to breathe again, softly, steadily, ready for the next chapter in its long and patient story. The earth had begun to recover from its first deep freeze. Ice melted back into water, sunlight once again reached the surface, and life resumed its slow, steady work. The world seemed calm, balanced, alive. But in the quiet cycles of chemistry and time, balance never lasts for long. What had risen now began to fall. Oxygen, which had once flooded the atmosphere in the planet's great awakening, started to vanish. Not all at once, but in a long and quiet decline, like breath leaving a body. It was a subtle change at first, invisible in the sky, unnoticed in the still seas, yet deep within the oceans, where chemistry rules more than light, the transformation had already begun. The cause was not a single disaster, but a series of small shifts that built upon each other. As oxygen grew abundant, it reacted with minerals in the crust, with gases in the air, and with organic matter sinking into the seafloor. The planet's own chemistry consumed what life had made. The balance between creation and destruction tipped, and slowly, oxygen was drawn back out of the air. The world dimmed again. Beneath the surface, the oceans grew heavy with iron and sulfur once more. Where blue water had shimmered, murk returned. In the deeper layers, oxygen disappeared entirely, replaced by gases that could not support most of the life that had adapted to breathe it. Microbes that once thrived on sunlight and air struggled to survive, while others, ancient kinds that had endured from the planet's earliest ages, returned to dominance. It was as if the Earth had taken a step backward in time, slipping from an oxygenated world back toward the chemistry of its youth. Scientists call this the oxygen crash, a time when the fragile atmosphere of the Proterozoic nearly collapsed. For the first time since life had changed the planet's air, that same life faced the possibility of erasing its own work. The oxygen that had once given the world color and clarity was fading, and with it, stability. The consequences reached far beyond the air itself. Without oxygen, much of the greenhouse gas balance shifted again. The planet cooled in some regions, while others grew stagnant under layers of still, dense air. The cycles that had carried nutrients through the seas began to falter. The once bustling microbial reefs thinned out, leaving behind emptier stretches of ocean. Whole ecosystems vanished without sound. There were no great extinctions in the way we know them now, no bones or fossils to mark the losses. But in the chemistry of ancient rocks, in the patterns of isotopes and minerals, the silence is recorded. For millions of years, the Earth lingered on the edge of suffocation, and yet, even in this near death, life adapted. The crisis forced evolution to change its rhythm once more. Deep in the ocean, in places untouched by sunlight, microbes began experimenting again with survival. Some learned to use sulfur instead of oxygen. Others found ways to live on traces of metals or hydrogen. The planet's metabolism diversified, even as much of its surface world grew still. The line between life and environment blurred, each adjusting, reshaping, and responding to the other. In these hidden laboratories of survival, new possibilities began to form. Cells that had once relied on simplicity grew more intricate inside, finding new ways to manage energy and shield themselves from the chaos of the changing world. The long decline of oxygen did not end life, it refined it. The Earth seemed fragile then, its atmosphere uncertain, its oceans layered with darkness and poison. But from within that instability, the seeds of complexity took root. The planet was learning that catastrophe could also be a teacher, that from scarcity could come invention. As the oxygen levels eventually began to rise again, the life that re-emerged was different, more efficient, more resilient. Cells that had learned to survive both abundance and deprivation carried within them the tools that would later build plants, animals, and all complex life. The crash had nearly undone the planet's greatest progress, but in the process, it had given evolution a new set of instruments to work with, new metabolisms, new genetic strategies, new ways of being alive. Above the seas, the air still shimmered pale and thin. The sunlight that touched the waves felt weaker, gentler, as if filtered through memory. Yet beneath that calm exterior, Earth's hidden life was already rewriting its destiny. The planet that had nearly died was breathing again, faintly at first, then more deeply. The cycles of air and stone began to stabilize once more, slower this time, steadier. The world had learned the fragility of its own breath, and in doing so, it had also discovered its strength. From collapse came renewal, from scarcity came invention, and from the edge of silence, the next great chapter of life was quietly preparing to unfold. The earth was restless beneath its calm surface. For billions of years, its heart had burned without pause, moving slowly, invisibly, beneath the weight of oceans and stone. The crust that formed the planet's skin was never still. It cracked and folded, lifted and sank, breaking itself apart and sewing itself back together again. From that deep, slow motion came something extraordinary, the first true continents. They began as fragments, scattered pieces of lighter rock floating above the denser crust below. Volcanoes fed them, adding layer after layer of new material as molten rock cooled and solidified. These early landmasses were small, rough, and barren, surrounded by endless seas. Yet over time, the movement of the Earth's interior drew them together. The planet's plates collided and merged in long, drawn-out embraces that took millions upon millions of years. Eventually, from this restless dance, a vast landmass began to form, the first supercontinent, known to science as Columbia or Nuna. It was not the world we know today. Its mountains were raw and jagged, its surface scorched by the sun and scoured by wind. There was no grass to soften the plains, no forests to sway in the air, no rivers carved by roots. The land was new, a landscape of bare stone and shadow. Yet even in that emptiness, change was taking place. When rain fell upon those first mountains, it began a process that would reshape both the land and the sea. Water ran down the slopes, dissolving minerals as it flowed, carrying traces of the continent back into the ocean. The rivers that did not yet have names brought with them elements that life had never tasted in such abundance: phosphorus, calcium, and iron, all of which would become nourishment for the living world. This simple act, the erosion of stone by water, became one of the planet's most powerful forces. Each drop of rain that fell, each grain of rock that drifted into the sea, was part of a silent exchange between Earth's surface and its oceans. Nutrients that had once been locked inside the crust were now free, spreading through the shallows and feeding the microscopic life that thrived there. For the first time, land and life were connected. The continents also began to influence the air. As rain washed minerals into the sea, carbon from the atmosphere dissolved in water and combined with rock, locking away greenhouse gases deep within the Earth's crust. The cycle was slow, almost imperceptible, but it helped regulate the planet's temperature. The Earth was learning to balance itself. Volcanoes released carbon dioxide into the air, and weathering drew it back down again. Together, These forces formed one of the earliest versions of what scientists now call the carbon-silicate cycle, the planet's natural thermostat. Over millions of years, this balance allowed the world to remain stable enough for life to continue evolving. Though storms came and glaciers advanced, the Earth no longer swung wildly between fire and ice. The continents, solid and enduring, acted as anchors of stability. But land was not only a chemical player, it became a stage for new possibilities. Tidal zones along the coasts, where sea met stone, formed unique environments. Waves crashed against rocks, spraying salt water into tiny pools that warmed in the sun. In these shallow, shifting worlds, life found new footholds. Microbes colonized the edges, forming films and mats that clung to wet surfaces. They learned to endure drying and flooding, preparing for challenges that life would not fully conquer until much later, when creatures finally stepped onto land for good. Even from a distance, the sight of Columbia would have been breathtaking. Vast mountain ranges rose from the ocean, their peaks dusted with volcanic ash. Rivers cut through valleys of black and gray stone, feeding into deep green seas. Lightning arced across skies filled with thin clouds, and at the boundaries where the plates collided, new volcanoes erupted constantly, pouring heat and minerals into both land and ocean. Beneath this surface activity, the Earth's mantle churned. Heat moved slowly outward, driving the plates like drifting rafts. The continents were not fixed. They slid across the globe, inch by inch, shifting with time. Even in their apparent stillness, they were alive with motion. Over the eons, this grand supercontinent would break apart and drift, its pieces wandering across the globe to meet again in different forms. Rodinia, Pangaea, Gondwana, each one a reflection of that first experiment in continental unity. But Columbia was the beginning. It was the first time the Earth gathered its strength into one great body of land, the first time mountains rose high enough to call out to the sky. With its birth, the planet gained a new dimension. It was no longer only a world of water and air. The continents gave the Earth texture, permanence, and complexity. They shaped weather, guided ocean currents, and carved paths for evolution to follow. The land had entered the story, and everything that lived would now feel its influence. From this moment on, life and stone would move together, one shaping the other, forever intertwined in the slow poetry of creation. For nearly 1 billion years, the Earth seemed quiet. After the birth of continents and the settling of the skies, the planet entered an age that, for a long time, scientists believed to be uneventful. They called it the boring billion, a stretch of time between roughly 1.8 and 800 million years ago, when at first glance, very little seemed to happen. The continents stayed mostly in place. The oceans did not boil or freeze. No great extinctions reshaped the biosphere. The world simply existed in a kind of still balance. Yet beneath this calm, invisible to any observer, the machinery of evolution and chemistry continued to hum. What looked like stillness was in fact preparation, a quiet gathering of energy, matter, and possibility. The continents of that time, bound together into the supercontinent Columbia, weathered slowly under gentle rains. Each droplet that fell carried with it tiny grains of rock, worn down from mountain peaks and carried into the sea. There, those minerals dissolved and mingled, feeding the ocean with nutrients. Over millions of years, the process repeated endlessly. What looked static from afar was, up close, a constant cycle of erosion, deposition, and renewal. Within the oceans, life continued its slow work. Microbes filled the water in unseen abundance. They formed mats along the seafloor and colonies within shallow bays, transforming sunlight and chemistry into energy. With each breath of photosynthesis, they released oxygen into the water, not enough to fill the atmosphere quickly, but enough to begin accumulating again. The oxygen did not rise evenly. In the deeper parts of the oceans, it was often consumed as quickly as it was made, locked away in chemical reactions with metals and sulfur. But near the surface, in the sunlit zones, oxygen slowly gathered over hundreds of millions of years. That thin layer of breathable water began to spread, setting the stage for the transformations that would one day follow. The planet's chemistry also began to shift in subtle but profound ways. New minerals formed on land, more diverse and complex than any before. These were born from reactions between oxygen, water, and the varied elements within the crust. It was during this long period of quiet that Earth's mineral diversity exploded, growing from a few hundred types to thousands. Each one held a record of its time. The atmosphere's condition, the movement of continents, the balance of elements in the sea. Meanwhile, deep within the oceans, evolution was experimenting. Cells were no longer simple structures. Some had begun forming internal compartments, tiny spaces that allowed them to control energy and chemistry more efficiently. Others started living in partnerships, one cell within another, trading protection for power. These early alliances would eventually lead to the first complex cells, the ancestors of all plants, animals, and fungi. It was a slow unfolding, so gradual that it would have appeared motionless if measured in human years. Yet in the scale of geologic time, it was an age of innovation. The building blocks of complexity were taking shape, molecule by molecule, inside invisible worlds. Above the surface, the land masses shifted almost imperceptibly. Mountains rose and wore away, rivers carved shallow valleys, dust blew across empty plains. The continents, covered in bare rock and streaks of mineral color, were largely lifeless, but they were changing the planet all the same. Their erosion regulated the carbon in the atmosphere, keeping temperatures steady. Their presence shaped the flow of winds and ocean currents, spreading nutrients from one side of the world to another. Even the calm had its purpose. Stability gave evolution the time it needed to refine what it had created. Without the chaos of constant catastrophe, life could experiment without being erased. Genetic innovation accumulated like quiet notes in a melody, waiting for the right moment to crescendo. From time to time, volcanic eruptions punctuated the stillness. They released pulses of carbon dioxide that warmed the air, then cooled again as the gases were drawn back into rock. The balance held. Oceans remained rich in iron, manganese, and other elements that kept microbial life thriving. The biosphere was small, but it was resilient. In this long and patient interval, the Earth became a kind of laboratory for complexity. Oxygen levels rose just enough to allow new metabolisms to form. Cells developed new ways to store information, repair themselves, and communicate. The architecture of future life was being drafted quietly, beneath a calm sky and a steady sun. To call this time boring is to mistake silence for emptiness. The planet was not asleep, it was thinking, slowly and deeply, in the language of chemistry and time. Every small change in the ocean's oxygen, every mineral crystal that formed and sank into sediment, was part of a vast, unseen story, unfolding beneath the stillness. When this long calm finally ended, the world that emerged was ready. The groundwork had been laid, the atmosphere had been tuned, and life had gathered the tools it needed to take its next great leap. The boring billion was not boring at all. It was the heartbeat between creation and transformation, the pause that allowed the earth to gather its strength before it breathed life into complexity. For billions of years, life on Earth had been small, simple, and solitary. The oceans were filled with single-celled organisms, drifting, feeding, dividing, and repeating. Each one was a world unto itself, carrying the instructions of survival written in the language of molecules. But deep within that simplicity, something extraordinary was waiting to unfold. At some quiet moment in that vast stretch of time, one cell met another. Perhaps it was an accident, one microbe drifting too close to another in the still waters of the ancient sea. Perhaps it was an act of hunger, a cell trying to consume another for energy. Whatever the cause, that meeting did not end as expected. Instead of one devouring the other, something miraculous happened. The smaller cell lived inside the larger one. It was a strange and delicate partnership at first, but it worked. The smaller cell found protection within its host, shielded from the harsh conditions outside. In return, it offered something precious: energy. This quiet union would become one of the most important moments in the history of life. It marked the birth of a new kind of organism, one built on cooperation rather than competition. This process, known to science as endosymbiosis, transformed biology forever. The smaller cell became what we now call a mitochondrion, a tiny power source living within the larger cell. Together, they formed the first eukaryotic cells, the ancestors of every plant, animal, and human that would ever exist. The oceans were still calm, the continents still drifting, yet beneath that tranquility, the rules of life were being rewritten. These new cells were no longer just chemical machines. They had compartments, each one performing a special task. They could store energy more efficiently, repair themselves more precisely, and handle more complex genetic information. For the first time, life could grow not only in size but in depth. Inside these early eukaryotes, the smaller mitochondria multiplied independently, each one a descendant of the ancient cells that had once lived freely in the ocean. They became inseparable from their hosts, passing from generation to generation as part of a new, shared identity. It was the beginning of something life had never tried before: the merging of separate beings into one harmonious whole. This cooperation unlocked possibilities that had never existed. With mitochondria producing energy so efficiently, cells could afford to build more complex structures. They developed internal skeletons of filaments to support their shape, and intricate transport systems to move nutrients within. They began storing their DNA within a protective core, a nucleus, where genetic material could be organized and guarded. In the quiet darkness of the ancient seas, evolution was no longer only about survival. It was beginning to explore beauty in function, symmetry, pattern, and coordination. Cells started forming colonies, groups that worked together as single units. They communicated through chemical signals, shared nutrients, and specialized their roles. Some grew larger, some smaller, each finding its purpose within the collective. The world had never seen such complexity. For billions of years, life had been a chorus of individual notes. Now, it was learning to compose harmonies. Energy control became the key. The mitochondria inside these new cells were powerhouses, generating more energy than any organism before them. That energy became the currency of evolution, funding the experiments of complexity, movement, sensing, reaction. Life was no longer bound by simplicity. It could now afford imagination. This partnership was not limited to mitochondria. Later, another great alliance would form when certain eukaryotic cells absorbed photosynthetic bacteria, which became chloroplasts, the green engines of plants. Through these layered acts of cooperation, the living world became a tapestry of shared histories, each organism carrying within it the memory of ancient unity. It is humbling to think that every breath, every heartbeat, every thought in our minds depends on that ancient pact. The energy that powers our cells still comes from the descendants of those tiny organisms that learn to live inside others. We are not separate from them. We are the continuation of that decision to coexist. If one could drift through the waters of that age, the change might not have been visible. The seas would have looked the same, gentle light filtering through the surface, plankton floating in quiet rhythm. But in every droplet, in every microscopic life form, cooperation was reshaping the future. The earth itself seemed to pause, letting this innovation take hold. The oxygen in the air continued to rise. Nutrients flowed from the continents into the seas. The conditions for life to grow more intricate were all falling into place. This moment, when one cell decided not to destroy another, but to live alongside it, was one of the most profound turning points in Earth's story. From it came every leaf, every fish, every bird, and every human who would one day look back and wonder how life began. The lesson written in that ancient sea was simple yet eternal. Survival is not only about strength or speed, but about connection. In a world shaped by fire and stone, it was cooperation, quiet, invisible, and patient, that changed everything. For billions of years, life had been multiplying in silence. Cells divided into copies of themselves, each one nearly identical to its parent. The process was simple, dependable, and patient. It had carried life through storms, freezes, and chemical chaos. But sameness has limits. In a world that was always changing, perfect copies could not always keep up. Evolution needed a new kind of experiment, a way for life to become more inventive. Somewhere in the deep oceans of the Proterozoic, nature found that answer. It began quietly within the mysterious interiors of the new complex cells. These were the eukaryotes, creatures that already carried partnerships within their walls, their power drawn from cooperation between once separate lives. Over time, they discovered another kind of union, one not of survival, but of renewal. Two cells came together, shared their inner instructions, and then created something entirely new. This was the invention of sex. It was not romance, not instinct, not even choice. Simply a new way for life to reshuffle its code. Where once each generation had been a reflection of the last, now every birth could be a variation, a surprise. Genes could mix, combine, and recombine, producing endless new possibilities. The first sexual reproduction was likely humble and microscopic, a chemical choreography performed by single-celled organisms drifting through the ancient sea. One cell merged with another, their nuclei exchanged fragments of genetic material, and then they parted, or divided again, each carrying a slightly altered version of what came before. It was an act of exchange and renewal, and it changed everything. Through this process, life gained imagination. Variation became the rule instead of the exception. Each generation could explore new forms, test new combinations, and adapt more quickly to the ever-changing world. Evolution, which had once been a slow drift guided by rare mutations, now became a dynamic dance. Diversity blossomed. In the calm oceans of that time, these new sexual cells began to outpace their simpler cousins. They could evolve faster, recover from stress more easily, and handle environmental shifts with greater grace. When the chemistry of the oceans changed or temperatures swung, they had more tools to survive, more possibilities written in their genes. It is almost poetic to think that such a simple act, the sharing of information, became the foundation for the richness of life that would follow. Every color in a bird's feather, every shape of leaf, every sound ever made by a living creature can trace its origin to that ancient exchange. Without it, evolution would have remained quiet, slow, and repetitive. The invention of sex was not only about adaptation, it was also about connection. Through reproduction, life learned to intertwine its lineages, to blend and merge across time. No living being would ever again be a pure copy of the past. Each would carry a blend of histories, memories written in DNA, threads woven from countless ancestors. With this new mode of reproduction came something else, a subtle sense of renewal. When one generation ended, the next did not begin from scratch. Instead, it carried forward the old, improved by the endless creativity of combination. Life had found a way to remain both constant and new. This change did not happen quickly. For millions of years, sexual reproduction existed side by side with simpler methods of cloning. It was a long experiment, tested in the quiet currents of the sea. Yet slowly, it spread, because those who shared their genes tended to thrive where others faltered. The earth itself rewarded diversity. As eons passed, this new power transformed evolution from a slow unfolding into a vibrant cascade. Populations could adapt to new climates, resist diseases, and explore new environments. The variety of life expanded, setting the stage for multicellular organisms and the complexity that would one day fill the oceans, forests, and skies. It was a gentle revolution, invisible but profound. No volcano erupted to mark its arrival, no flash of light announced it. Yet from that moment on, every form of life that followed, every coral, fern, insect, fish, and mammal, would inherit the gift of diversity born in those ancient waters. Sex, at its core, was nature's way of introducing surprise. It ensured that no two creatures would ever be exactly the same. It filled the world with difference, with resilience, with beauty, and though it began in the stillness of the Proterozoic seas, its influence would ripple outward forever. The cells that first learned to share would one day give rise to the great web of life itself, connected, intertwined, and endlessly varied. Through them, the earth found not just a way to survive, but a way to grow more intricate, more creative, and more alive with every passing age. In the long history of our planet, few moments reshaped existence so completely. The invention of sex was not just a new way to reproduce. It was the dawn of diversity, the quiet spark that would light the path toward the infinite forms and faces of life that now fill the world. Life had learned to share its essence through sex, mixing its codes and creating endless variety. Now, the next step in that quiet story was waiting, a deeper form of togetherness. It began, as many things in nature do, with cooperation. The oceans of the Proterozoic were calm and rich, with microscopic life. Sunlight filtered gently through the water, scattering golden beams across drifting colonies of cells. Each one floated freely, feeding, dividing, and adapting. Yet, among them, a new kind of relationship began to take shape. Some cells found safety in numbers. Instead of drifting apart after dividing, they stayed close, their membranes touching, their work beginning to overlap. At first, these gatherings were loose and temporary, a cluster here, a filament there, drifting with the tides. But over countless generations, these small partnerships grew stronger. The cells began to communicate through chemicals, passing signals and sharing resources. They discovered that by living together, they could survive better than they could alone. These were the first ecosystems, not grand forests or coral reefs, but delicate networks of cells, each doing its part in an invisible web beneath the sea. The simplest of them formed thin mats on the ocean floor, shimmering with faint color where sunlight reached. Others built floating clusters, small enough to pass unnoticed, yet vital to the planet's unfolding story. Within these groups, cells began to divide their labor. Some specialized in gathering light, others in storing energy or protecting the colony's surface. It was not yet true multicellularity, but the idea of it was growing, the sense that unity could be more powerful than solitude. This shift, from independence to cooperation, marked another turning point in evolution's patient rhythm. It was the moment life began to realize that survival was not always about competition. It could also come from connection. Over time, certain colonies evolved tighter bonds. Their cells became more interdependent, connected by threads of proteins and sugars. Communication deepened. Signals moved from one cell to another, telling them when to grow, when to divide, when to rest. Slowly, individuality began to blur. In some of these organisms, certain cells gave up their ability to reproduce, focusing instead on structure or defense. Others became specialized for movement, waving tiny filaments to help the colony glide through the water. This was the birth of organization. The first whispers of body plans that would one day fill the world with shape and motion. The seas that once belonged to single, solitary cells were now alive with communities, each one a small city of cooperation, invisible yet vast in significance. Where once there had been countless individuals competing for the same patch of light or nutrient, there were now societies of cells, each playing a role in harmony. These early cooperative forms became the foundation for multicellular life. They were not yet animals or plants, but they carried within them the blueprint for both. In their silent union, the rules of life changed. No longer was existence limited to what one cell could achieve. The potential of many had become infinite. Imagine drifting through those ancient waters. The surface above glows softly, streaked with light from a pale sun. Below, the seabed is carpeted with microbial colonies, sheets of life layered across rock, undulating gently with the tide. Each ripple of water carries nutrients, and each flicker of sunlight powers the delicate balance below. It would seem quiet, but within that silence, billions of cells were whispering to each other, exchanging signals in a language written long before words existed. That language was chemistry, the universal tongue of life, carried in molecules and reactions that bound the ocean into a single living system. As the colonies grew, so too did the complexity of their surroundings. Waste from one species became nourishment for another. Layers of microbial mats formed ecosystems that recycled matter endlessly. Each death became the seed for new life, and each breath a contribution to the world's changing atmosphere. This invisible cycle, repeated countless times, began to knit the biosphere together. It was the first web of life. Fragile, microscopic, but complete. Every organism played its part, whether it knew it or not. The balance between creation and decay, energy and rest, had found its rhythm. From this slow, steady cooperation, multicellular life emerged. Cells that had once lived as individuals now fused into one body, their identities woven into the whole. These new beings could grow larger, move with purpose, and explore parts of the environment that single cells could not. It was a revolution not of power, but of unity. The oceans that had once shimmered with countless single sparks now glowed with clusters of light moving as one. Through the still waters of the Proterozoic, life had learned something profound. That survival was not just about enduring the world, but about building connections within it. Every partnership, every shared function, every silent signal between cells was a step toward the boundless complexity that was still to come. The first ecosystems were not grand, but they were alive in every sense. They carried the seeds of every forest, every coral reef, every living network that would ever exist. The world was beginning to pulse as one body, one breath, one delicate harmony of living things bound together beneath the sea. And in that soft union, life discovered its most enduring truth, that together it could create more than any single cell could dream alone. The world had grown old and wise since the time of its first continents. The seas were alive with quiet cooperation, the air thin but stable, and the crust beneath everything continued its endless motion. Deep inside the planet, slow rivers of molten rock carried the continents like rafts across a restless sea of stone. Every inch of land was on a slow journey, drifting, colliding, and reshaping the face of the earth. Over countless millions of years, these wandering continents drew closer together. What began as scattered islands and small plates gradually merged, grinding and folding into a single vast expanse of land. Mountains rose higher than any before them. Volcanoes traced fiery lines along the edges of colliding plates, and deep beneath the surface, heat and pressure forged new minerals that shimmered in the dark. This was the birth of Rodinia, the great supercontinent. Its name, chosen much later by humans, means motherland, and in many ways it was. For the first time in the planet's history, nearly all land was joined as one. It stretched from pole to pole, an immense and varied world of rock, mountain, and shallow inland seas. The coastlines curved in endless arcs, and beyond them, the global ocean spread vast and deep, encircling the single landmass like a blue halo. To imagine Rodinia is to see a planet both familiar and strange. Its heart was made of towering mountain ranges, formed by the crush of continents colliding. Valleys and basins cut between them, filled with rivers and shallow seas. The air above those mountains shimmered with dust and volcanic gas, while the edges of the land were washed by tides stronger than ever before. The ocean currents that wrapped around Rodinia moved heat and salt in complex patterns, shifting the climate in ways the world had never experienced. The interior of the supercontinent was dry and extreme. With so much land gathered together, moisture from the oceans rarely reached the center. Deserts spread across its middle, while coastal regions pulsed with storms. In some places, glaciers grew at high altitudes, while in others, the ground baked beneath a relentless sun. The earth was learning what it meant to balance itself on such a grand scale. The creation of Rodinia changed everything, not only the shape of the planet, but the flow of its air and sea. When continents cluster together, they interrupt the global conveyor of ocean currents that move warm and cold water around the world. This new arrangement began to alter the planet's temperature. The great ocean that surrounded Rodinia, called Mirovia, carried cold water to the poles more efficiently than ever before. Slowly, the earth began to cool again. At the same time, the mountains of Rodinia began to weather. Rain and wind wore them down, washing vast quantities of minerals into the sea. This process drew carbon dioxide out of the atmosphere, one of nature's quietest and most powerful forms of climate control. With less carbon to trap heat, the world cooled further. Rodinia had unified the planet's land, but in doing so, it set the stage for another of Earth's great transformations. The life that thrived in the oceans below adapted to these changes. Microbial mats grew along the supercontinent's coasts, feeding on minerals carried by rivers and tides. Cyanobacteria and other photosynthetic life continued to fill the atmosphere with oxygen, while deeper waters became home to more complex microbial communities. The world beneath the surface remained vibrant even as the air above began to chill. Over tens of millions of years, Rodinia began to shift again. The same forces that had created it continued to move beneath its foundations. The crust pulled and stretched as new rifts opened, splitting valleys and widening faults. Lava seeped up through cracks, forming chains of volcanic islands and filling the skies with ash. Slowly, the vast supercontinent began to tear itself apart. The breakup of Rodinia would become one of the most significant events in Earth's history. As the land fractured, new coastlines formed, and ocean circulation changed once more. The continents drifted into new positions, disrupting the balance of sunlight and heat across the globe. Temperatures plummeted, glaciers advanced from the poles, and the world began to freeze again. This slow disassembly of Rodinia likely helped trigger one of the planet's most dramatic ice ages, a deep freeze that would one day wrap the world in snow and silence. But for now, in this chapter of the Earth story, Rodinia still stood proud, stretching across the globe like a sleeping giant. Its mountains pierced the thin blue air. Its rivers carried minerals into hungry seas. Its valleys echoed with wind that had crossed half the planet. It was a world of extremes, of contrasts, of slow and patient motion. The earth was testing the limits of its own balance, binding together, breaking apart, and beginning again. And, beneath it all, the same quiet rhythm continued, the same pulse that had carried life from its earliest whisper. Even as continents collided and separated, the oceans below remained alive, waiting for the next turn in the planet's long and patient dance. The slow drifting of Rodinia had stirred the planet's balance once again. As the continents pulled apart, new oceans formed, and the chemistry of the atmosphere shifted in ways that would soon test every living thing. The world, once alive with light and color, began to dim. The earth was cooling. It began softly, almost invisibly. Temperatures fell a little each century, then a little more. Clouds thickened, the sunlight weakened, and snow began to linger longer each season. Polar ice stretched toward the equator, brightening the planet's surface with mirrors of frozen light. The more the Earth reflected the sun's warmth back into space, the colder it became. It was a self-feeding spiral, a slow descent into stillness. And then, at last, the seas began to freeze. This was the cryogenian period, a time unlike any other in the planet's long history. Glaciers grew until they met at the equator, wrapping the world in a shell of white. The oceans, once a deep sapphire blue, were sealed beneath thick layers of ice. The continents lay buried under snowfields that stretched endlessly in all directions. Winds howled across frozen plains, carrying dust and ice crystals that glittered beneath a dim, pale sky. The earth had become a snowball, a silent, gleaming sphere of ice turning slowly in the darkness of space. Sunlight that reached the surface bounced away, trapped by the planet's own brilliance. Even the air itself grew thin and dry, locked into glaciers. The atmosphere held so little moisture that clouds became rare. It was as though the planet had exhaled and forgotten how to breathe again. For life, it was a time of unimaginable trial. The oceans beneath the ice remained liquid in their depths, kept from freezing solid by the slow warmth of the planet's core. But light could no longer reach those waters. Photosynthetic organisms, once thriving near the surface, vanished into the shadows. Most of the planet's seas were silent, still, and dark. Yet even in this frozen world, life endured. It found refuge in hidden corners, where warmth and chemistry persisted, near the cracks in the ice, where the ocean occasionally touched the open air. Microbes gathered around pockets of faint sunlight, clinging to the last traces of energy. In the blackness of the deep sea, hydrothermal vents continued to pulse with heat from within the earth. Around them, microbial communities fed on minerals and sulfur, living without the need for light. These vents became sanctuaries of survival, small islands of warmth in a planet-wide ocean of ice. Even in shallow coastal pools, life persisted. Volcanic activity and tidal shifts sometimes broke through the frozen crust, creating temporary pockets of liquid water. In these rare and fragile environments, the rhythm of biology continued, slow but unbroken. It is easy to imagine that the world was silent then, but silence is not the same as death. Beneath the ice, the planet was still alive. The slow churn of its molten heart, the steady release of heat through cracks and vents, and the stubborn persistence of microbial life all whispered that the story was not over. Over millions of years, the frozen world endured. Ice reflected nearly all the sunlight that touched it, preventing warmth from returning. The earth was locked in feedback, cold creating more cold. Yet below the surface, volcanoes continued to erupt. Carbon dioxide and other gases poured into the air, building slowly because there was no rain to wash them away. Time moved in silence. The white planet circled the sun again and again, waiting. Then, at last, the balance began to shift. As greenhouse gases built up in the atmosphere, the planet's icy grip began to loosen. The faintest warming melted the first few meters of ice, darkening patches of the surface and allowing sunlight to sink in instead of reflect away. More melting followed, and more warmth. The feedback reversed itself. Suddenly, the earth awakened from its deep freeze. Glaciers collapsed into torrents of water. Oceans swelled and roared, breaking free of their icy prisons. The atmosphere filled with steam, and carbon dioxide trapped the returning heat. For a time, the world swung wildly to the other extreme, a greenhouse planet born from the ruins of ice. The snowball Earth catastrophe had ended, but its legacy would remain forever. For the organisms that had survived, the experience had changed everything. Those that endured had adapted to extremes of cold, darkness, and scarcity. They had learned resilience. Their descendants would carry that endurance forward into every lineage that would follow. When the ice retreated and sunlight once again flooded the seas, the world that emerged was new. The oceans were rich with nutrients released from glaciers, fueling explosions of life. Evolution, which had once crept slowly, now surged forward, armed with diversity born from survival. The earth, in nearly dying, had taught life how to live. The cryogenian freeze was not an ending, but a transformation, a long breath held between two worlds, one simple and microbial, the other complex and awakening. From the silence of ice came renewal, and from that renewal, the next great steps in evolution were waiting quietly beneath the thawing sea. Beneath the planet's frozen surface, the Earth was still alive. Even during the long silence of the cryogenian ice, its heart had never stopped beating. Deep underground, molten rock churned and pressed against the crust, searching for release. The world above may have been white and lifeless, but below the glaciers, fire still moved in the dark. For millions of years, volcanoes erupted into that frozen stillness. Their voices were muffled by the ice, their smoke swallowed by the thin atmosphere. But their work continued patiently. Each eruption poured carbon dioxide into the air, a gas that trapped heat. Normally, this carbon would have been balanced by rain, plants, and the slow recycling of rock, but now the cycle was broken. The world's surface was sealed under ice, and there was no weathering, no living forests to absorb what the volcanoes released. So the gases gathered, slowly thickening the sky. Each eruption added another thin veil of warmth the heat could not yet pierce, the vast white shield that covered the planet. But it lingered, gathering power. The Earth was doing what it always had in times of imbalance. It was adjusting, patiently, through its own deep mechanisms. The process was unimaginably slow. Millions of years, measured in breaths of fire and frost. But eventually, the carbon dioxide grew dense enough to trap sunlight once again. The greenhouse effect, faint at first, began to spread its fingers across the ice. The cold that had locked the planet began to weaken. At first, only the equatorial regions softened, the ice thinning by inches over centuries. Then, as the warming continued, patches of dark rock and shallow meltwater appeared, where the ice turned to water. The planet's surface darkened. It no longer reflected sunlight back into space. Instead, it absorbed the light, deepening the warmth. The balance tipped. The ice began to retreat. When the thaw came, it was not gentle. It was an awakening. Rivers of meltwater roared down the slopes of buried continents. Glaciers collapsed into the sea with a thunder that would have echoed across the planet. The oceans, once sealed and silent, cracked open to the sunlight. Steam rose in vast curtains, and the atmosphere thickened with moisture. The greenhouse heat surged. For a time, the earth swung to the other extreme. Temperatures soared. Rain fell for ages, washing across the continents, dissolving minerals from stone and carrying them into the seas. These minerals, rich in iron, phosphorus, and nutrients, flooded into the oceans, feeding the waiting life that had endured beneath the ice. Beneath the thawing waters, microbes awoke from their long dormancy. The cyanobacteria, those quiet architects of oxygen, found their strength again. With sunlight pouring freely through the surface, they began to bloom. Vast mats of life spread across the shallows, turning the oceans green and gold. Oxygen surged into the air once more, transforming the chemistry of the world all over again. The atmosphere, once thin and pale, grew rich and blue. With oxygen came ozone, a fragile shield that formed high above the clouds, protecting the surface from the sun's harsh radiation. It was as if the planet, after nearly dying, had rebuilt its lungs. This sudden flood of oxygen would reshape evolution itself. It opened the door for larger, more complex life to thrive. The ancient single cells that had survived the ice now faced a new world of abundance, one filled with opportunity, but also new challenges. Energy was easier to harvest, but oxygen was also a powerful and dangerous gas. Organisms had to learn to master it, to use it carefully without being destroyed by it. In the grand rhythm of Earth's story, catastrophe had become renewal. The very forces that nearly ended life had given it everything it needed to flourish again. The volcanoes that had burned beneath the glaciers were the planet's secret guardians, slowly preparing the world for its next awakening. As the centuries passed, the ice sheets withdrew completely, leaving behind a landscape carved and cleansed by their passage. The continents were reshaped by erosion, and the oceans sparkled beneath clear skies. The climate stabilized, though warmth still lingered, and the world entered an age of calm. From orbit, had anyone been there to see, the transformation would have been breathtaking. The Earth, once white and silent, had turned deep blue again, its land tinted with the subtle hues of minerals and early microbial life. Clouds swirled in soft spirals, tracing the path of winds that carried moisture and warmth across the globe. In that fragile balance between fire and ice, the planet had found renewal. The oxygen-rich atmosphere that now surrounded it would soon become the foundation for a revolution in biology. Complex cells, multicellular organisms, and eventually, the first visible forms of life would rise in its wake. It was a reminder written into stone and air alike, that destruction and creation often share the same source, the same volcanic breath that once darkened the sky now filled it with the gases of life. The same fire that had threatened to suffocate the world had melted its prison of ice. The earth had nearly frozen itself into stillness, but through the quiet persistence of its inner fire, it had rediscovered its warmth. From that warmth came motion, from motion came balance, and from balance came life renewed. And so, the planet turned once more beneath the sun, breathing again, its oceans alive with color and possibility. The age of survival had ended. The age of expansion was about to begin. When the great glaciers finally surrendered their grip, the Earth exhaled for the first time in millions of years. The white shell that had wrapped the planet melted into rivers, lakes, and oceans, and the sunlight that had long been reflected away now reached deep into the water once again. The thaw was not quiet. It was the sound of water meeting warmth, of ice collapsing into motion, of the planet awakening after a long and dreamless sleep. From space, the transformation would have been breathtaking. The once frozen sphere of pale light darkened into rich blues and soft greens. Clouds swirled across open seas, tracing new patterns of heat and wind. The continents, carved by ice and sculpted by meltwater, gleamed with fresh minerals. Everything on Earth was changed, and yet, beneath the surface, something familiar was stirring. Life had survived. The microbes that had endured the age of ice, hidden in deep sea vents, trapped in sediments, or clinging to patches of liquid water, now found themselves in a world overflowing with possibility. The meltwater carried with it a flood of nutrients: phosphorus from rock, iron from dust, and carbon washed loose from the continents. These elements poured into the seas like food for the waiting cells, and what followed was one of the greatest blooms in Earth's history. The oceans came alive again. Microbial life spread like wildfire through the newly open waters. Cyanobacteria, those ancient oxygen makers, once again covered the shallows, painting the seas with shades of turquoise and green. They multiplied with astonishing speed, forming great floating mats that drifted in the sunlight. Below them, in darker depths, other microbes fed on the nutrients that rained down, building invisible ecosystems layer by layer. The chemical balance of the planet began to change once more. Oxygen levels, which had fallen during the long freeze, now surged upward. With every breath the microbes released, the air grew richer and clearer. For the first time, since the ice had locked the world away, oxygen began to spread, not only through the water, but also across the sky. The planet's atmosphere stabilized, its chemistry finding a fragile harmony. The sunlight that filtered through the air was now shielded by a thin but growing layer of ozone, formed from oxygen itself. This invisible barrier softened the sun's harsh radiation, creating a safer world for life near the surface. For the first time, the planet was not only habitable, but hospitable. In this new balance of warmth, light, and chemistry, life began to explore its limits. Single cells started to group together, finding strength in cooperation. Colonies formed in the shallow seas, each cell taking on a different role, some gathering energy, some building structure, others simply keeping the rhythm of the community alive. These early partnerships laid the groundwork for the first multicellular organisms. The oceans of the Proterozoic now shimmered with quiet activity beneath the waves, unseen to any eye that would ever look back. Evolution was practicing complexity. The foundations of future animals and plants were being written, gene by gene, within these soft-bodied pioneers. The diversity that followed was not yet visible in form, but in chemistry, in potential, in the deep hum of life growing more intricate with each generation. Meanwhile, the continents themselves were awakening. Erosion carried minerals into the sea, feeding the marine world. Rivers traced new paths across fresh land, while volcanoes continued to breathe carbon into the air, balancing the planet's warmth. The Earth, which had so recently been trapped in silence, was now a system in motion, self-regulating, dynamic, alive. The oxygen-rich world that was forming would not only sustain the microbes that created it, but would soon allow entirely new kinds of life to exist. The increase in energy made possible by oxygen opened a door that had never before been accessible. Larger, more complex cells could now afford to evolve. cells that stored more information, that built structures, that coordinated their efforts with purpose. From this came a quiet revolution. The ocean floor, once barren, now shimmered with thin films of microbial communities. The water itself teemed with life too small to see, but abundant enough to alter the planet's chemistry. Every breath of oxygen, every flicker of light captured by photosynthesis was a step toward complexity. It is tempting to think of this time as peaceful, but beneath its calm surface, evolution was working tirelessly. The great bloom of microbial life was more than a recovery. It was a transformation. The planet had been reforged by catastrophe, and in that refounding, life had become more adaptable, more inventive, and more connected to the cycles of the Earth itself. As oxygen filled the air, the skies deepened to their modern blue. The seas, once red and heavy with iron, now glowed with clarity. Light could reach deeper than ever before, fueling ecosystems from surface to seafloor. The Earth, reborn from ice and fire, was now ready for its next chapter, the rise of visible life. But for now, in this moment of balance and abundance, the world was quiet. The continents rested under a warm sun, the oceans rippled with color and energy. The air was rich, the currents stable, the chemistry perfect. It was the calm before the next transformation, a world newly alive, breathing steadily, its pulse strong and full. The planet had not merely survived the ice, it had emerged from it renewed, wiser, and ready to create forms of beauty it had never known before. For a long while after the thaw, the world remained peaceful. The oceans were calm, rich with oxygen and life too small to see. Sunlight rippled through clear water, touching layers of green and gold microbes that drifted like dust motes in liquid light. The earth had steadied itself. The chemistry was balanced. The air was breathable. The stage was finally ready for something entirely new to appear. Life had spent billions of years perfecting its simplest forms. It had learned how to survive in fire, in ice, and in the silent depths of the sea. It had learned to share energy, to reproduce, to cooperate. Now, at last, it was ready to build upon that foundation, to weave simplicity into structure, and structure into something greater. The first whispers of complexity began within the cells themselves. Inside their delicate membranes, genetic material became more organized, more controlled. Instead of acting like solitary wanderers, these cells began following patterns, guided by a growing internal order. They started to specialize, dividing labor in subtle ways. One cell would handle energy, another structure, another communication. For the first time, the idea of a body, many working as one, was beginning to take shape. These early multicellular organisms were tiny, soft, and fragile. Most were smaller than a grain of sand, their forms faint outlines of the future. Some were simple clusters of identical cells. Others began to experiment with structure, forming hollow spheres or layered sheets that folded and curled in graceful shapes. Within these folds, cooperation deepened. Each cell sensed its place and purpose, responding to gentle chemical whispers from its neighbors. From these quiet signals, something remarkable began: organization. Instead of chaos, there was coordination. Instead of identical repetition, there was variation. Cells forming tissues, tissues creating patterns, patterns hinting at form. The world's first bodies emerged, not yet animals or plants, but something in between. They floated in the shallows, bending with the currents, absorbing nutrients through their soft surfaces. Their lives were brief, but within their simplicity lay the blueprint for everything to come. It is easy to imagine the oceans of that time, warm, glowing, and filled with unseen activity. A closer look would reveal the beginnings of movement. These early multicellular forms pulsed gently, responding to changes in light and temperature. Some stretched and contracted like breathing. Others glided slowly across the seabed, following gradients of food or light. They were the first creatures to experience coordination not just within a single cell, but across many. Inside them, evolution was quietly experimenting with control. Genes no longer worked alone. They turned on and off in intricate sequences, shaping growth and behavior. This was the birth of genetic regulation, a kind of choreography that allowed life to develop, shape, and form. With each generation, this dance became more precise, more beautiful, more full of possibility. The multicellular world was unlike anything before it. It was not yet filled with competition or predation. It was a world of exploration where life was simply learning what was possible. Each new form was an experiment, testing the boundaries of structure and stability. Some grew larger, some formed filaments that reached toward the light. Others clumped together, forming blobs and sheets that clung to rocks and sediments. From these humble beginnings came the first true organisms, entities greater than the sum of their parts. They were soft and silent, without bones or shells. Their bodies were made entirely of living tissue, flowing with water and nutrients. If you could have seen them, they might have looked like ribbons, bubbles, or tiny veils drifting through the sea. Each one was a small miracle of cooperation. Every cell within it was alive, yet none survived alone. Together, they created tissues that could grow, repair, and adapt. The boundary between individuality and unity began to blur. A new kind of life was taking shape, one that required trust between its parts. This was the dawn of complexity. The oceans, once ruled by single cells, now shimmered with forms that moved as one. It was as if the planet itself had begun composing with new instruments. The rhythm of life deepened, its harmonies richer and more intricate. Though these early creatures were small, their influence was vast. They altered the flow of nutrients in the sea, created new habitats, and formed the first true ecosystems built upon cooperation. The world was becoming more layered, more connected, more alive. The chemistry of existence had become biology. The transition from single cells to multicellular beings was one of the greatest transformations in Earth's history. It was not a leap, but a slow and patient unfolding, guided by time and chance, the same currents that once carried drifting. Microbes now carried the ancestors of every complex creature that would ever exist. From these soft and fragile beginnings, the roots of all future life were set. The animals, plants, fungi, and every living being that would one day breathe and move owed their existence to these early experiments in togetherness. In the gentle waters of the Proterozoic world, life had learned its most powerful lesson yet, that strength could come not from isolation, but from unity. And in that quiet unity, the earth began to imagine forms it had never seen before. In the quiet depths of time, after the world had warmed and the oceans had filled once more with light, something extraordinary began to unfold. For billions of years, life had been invisible to the naked eye, soft, microscopic, drifting silently through the sea. But now, in the gentle shallows of the late Proterozoic, the first creatures large enough to be seen were beginning to stir. The world they inhabited was calm and strange. The continents had settled into new shapes, washed by warm tides and blanketed in soft microbial mats that covered the seafloor like living carpets. The oceans shimmered with oxygen, the air held a quiet balance, and sunlight filtered gently through the water. There were no fish, no shells, no coral, only a soft, alien world of gentle textures and simple movements. And upon that stage, the first forms of visible life appeared. Their names, given much later by human hands, would sound almost poetic: Dickinsonia, Sprigina, Charniodiscus, Tribrachidium. They were the pioneers of complexity, the first creatures to give shape to what had long been only imagination. Their bodies were soft and symmetrical, their outlines etched like delicate impressions in sand. Some were flat and oval, rippling across the seafloor like living quilts. Others stood upright, anchored to the ground by stalks that swayed gently with the currents. Dickinsonia was among the most iconic of them all, an oval shape divided into segments that curved like the ribs of a leaf. It moved slowly across the seafloor, feeding on the thin layers of microbes that coated the sediments. It left faint trails behind, the first signs of purposeful motion etched into the mud of the ancient world. Nearby, Sprigina glided like a ribbon, its segmented body tapering into a head-like front. Some scientists believe it may have been one of the earliest creatures to possess bilateral symmetry, a left and right side, mirrored and balanced, a design that would one day define most animals, including us. Around them, other forms lived rooted in place. Charniodiscus resembled a feather or a frond, anchored to the seabed by a thin stem. It absorbed nutrients directly from the water, swaying softly in the currents that carried life's chemistry across the ocean floor. Some creatures, like Tribrachidium, displayed perfect radial symmetry, their bodies spiraling outward like three-armed pinwheels. Each one was an experiment in design, a glimpse of evolution's imagination testing new possibilities. This was the Ediacaran period, the closing chapter of the Proterozoic, and the dawn of visible ecosystems. For the first time, life formed entire communities. The ocean floors were no longer barren or silent, they pulsed with activity. Mats of microbes provided food for the grazers. Filter feeders drew sustenance from the passing water. Some creatures moved in search of nourishment, while others waited patiently, letting the world flow through them. It was the first time energy truly circulated through an organized web of life. The earliest food chains began here, simple yet profound. One organism consumed another's waste, another scraped nutrients from the surface below, and together they created cycles of matter and renewal. And within this new web came a quiet tension, the beginning of predation. For most of Earth's history, life had not needed to fear, but now, as creatures moved and fed, the possibility of hunting arose. Some organisms evolved thicker skins or buried themselves slightly beneath the sediment. Others grew faster or developed subtle ways to sense changes in their surroundings. The first instincts of survival, movement, reaction, awareness, began to appear. It was not yet violence as we know it, but something more delicate. The world, learning to respond. The seas of the Ediacaran would have been breathtaking to behold. Imagine drifting over a shallow ocean floor bathed in soft light. The surface below glows faintly pink and gold, rippling with mats of microbial life. Rising from it are shapes unlike anything alive today. Fans, discs, fronds, and spirals, all swaying gently as if breathing in unison. Nothing moves quickly, yet everything is alive, pulsing with silent purpose. Each creature depends on the others, forming a living tapestry across the seafloor. Some grow tall to reach the currents, others sprawl across the sediment, collecting food from below. Together, they create Earth's first ecosystems built on structure, balance, and interconnection. Within this calm and alien world, the concept of individuality began to shift. No longer were living things only single cells or simple clusters. Now, they were organisms with shape, behavior, and identity. The first nervous systems were still far in the future, but already the foundations of sensation were stirring. Cells that could react to light, to touch, to chemical traces in the water. It was here, in these soft and silent seas, that consciousness began to flicker, not in thought or awareness as we know it, but in motion, response, and connection. Life had begun to sense its surroundings, to interact, to move with intent, and so the Earth, after billions of years of chemistry and patience, had given rise to something new. The Ediacaran world was its first dream of complexity, a landscape of living fabrics and flowing designs, where the boundaries between form and motion blurred like ripples on water. It was a calm and alien paradise, quiet but alive with potential. Beneath its stillness, evolution was preparing for its next great experiment. The world had learned to build shapes. Soon, it would learn to fill them with motion. Before color, the ancient oceans were worlds of muted tones, soft greens, faint browns, and shifting grays beneath a pale light. The early seas shimmered with life, yet to the naked eye, it might have seemed as though the planet had not yet discovered its palette. But deep within those waters, in the hidden language of molecules and sunlight, color was already being born. The first pigments appeared quietly, like whispers between light and chemistry. They were not made for beauty, not at first. They were tools, molecules designed by living cells to capture energy, to protect, and to survive. Yet in doing so, they painted the seas with the earliest hints of blue, green, and violet. It began with sunlight. The earth, now rich in oxygen and clear skies, glowed with brightness. Sunbeams reached deeper into the water than ever before, scattering into soft blues as they sank. Life, already thriving in the shallows, adapted to this new clarity. Some microbes learned to harvest the sun's energy more efficiently, creating pigments that absorbed specific wavelengths of light. The most powerful of these pigments was chlorophyll, a molecule that transformed sunlight into sustenance. It absorbed the reds and blues, reflecting green, giving the oceans a new hue. Where once the water had been dull or cloudy, it now shimmered with life's reflection, a faint, glowing green that deepened with every passing age. But chlorophyll was only the beginning. Other pigments followed, each crafted by evolution's slow and patient hand. Some, like carotenoids, reflected shades of orange and gold, acting as tiny shields that protected cells from too much light. Others, like phycobilins, absorbed colors that chlorophyll could not, painting certain microbes in tones of crimson and deep violet. Together, these pigments formed an unseen rainbow beneath the waves. To an observer drifting through those Proterozoic seas, the world might have appeared softly iridescent, layers of blue-green, mats gleaming in the sunlight, purple films spread across stones, golden flares catching the light in the shallows. The chemistry of life had become art. Each color told a story of survival. The blue-greens belonged to the photosynthesizers, the oxygen makers that filled the air with breath. The purples and reds belonged to microbes that lived in the dimmer, deeper waters, capturing what light remained after the upper layers had taken their share. The golden tones shimmered in the balance between energy and protection, a warning that too much light could be as dangerous as too little. And so, the world became layered not only in form, but in hue. In this new spectrum of existence, color became both function and expression. The pigments that protected life from the sun's harsh rays also gave it personality. They turned survival into beauty and necessity into design. The play of light and pigment transformed the oceans into living mosaics. Waves of cyanobacteria drifted across the surface, their greenish glow mingling with violet reflections from deeper waters. In the stillness of tidal pools, colors rippled as organisms shifted and grew. When the sunlight faded each evening, the pigments continued their quiet work, storing energy, shielding cells, waiting for dawn to return. This evolution of color was not limited to the sea. The atmosphere, now rich with oxygen, allowed sunlight to scatter in ways that painted the entire planet. The sky deepened into the familiar blue we know today, a sign that oxygen and ozone had reshaped the world. Even the land, bare and rocky, was touched by this transformation. Minerals oxidized in the air, turning red and brown, rusted reminders of the same chemistry that fueled life below the waves. For the first time, the earth was not only alive, but beautiful. The emergence of color marked a turning point in the relationship between life and light. Before, sunlight had been something to endure or avoid. Now it became the primary source of energy, the rhythm by which life lived. Day and night gained meaning, warmth carried purpose, and light itself became the language through which the planet thrived. Even the earliest multicellular organisms were shaped by this colorful revolution. Their tissues began to contain pigments too, reflecting the environments they lived in. Some used color to protect themselves, others to absorb energy more efficiently. The beginnings of pattern, tone, and shade were forming, foundations for the endless diversity of color that would one day fill the world. To think that all of this, every vivid reef, every green forest, every painted sky, began with tiny molecules floating in the sea is humbling. Those early pigments were the first artists of the earth, transforming physics into poetry, chemistry into light. If you could stand by the shores of the late Proterozoic and look out across the water, you would see a world both familiar and foreign. The waves would shimmer with strange hues, soft and shifting under a pale sun. The air would feel new, the light gentle but full of promise. Beneath the surface, color would bloom quietly, alive and purposeful, each tone a note in the symphony of life. The chemistry of color had changed everything. It was the meeting point of energy and expression, of science and art. What began as protection became beauty, and what began as necessity became identity. The earth had found a new way to speak, not in sound or motion, but in light itself. And from that silent language of color, the planet's imagination had only just begun to unfold. Long before forests spread their canopies or animals stirred the oceans, the planet was already being shaped by invisible hands. They were small beyond sight, fragile beyond measure, yet together they built and maintained the world. These were the microbes, the planet's first and most enduring architects. They had been present since the earliest whispers of life, and through every transformation since, they never vanished. While continents collided and broke apart, while oceans froze and thawed, the microbial world remained, adapting to each change with quiet precision. By the time complex creatures began to evolve, the microbes had already built the stage they would live upon. It was their unseen chemistry that made the earth stable, breathable, and alive. Every breath of oxygen, every drop of rain, every grain of soil still carries their influence. The great cycles that sustain the planet, carbon, nitrogen, oxygen, all trace their origins back to these ancient engineers. Within the oceans, bacteria worked like living machines. Some captured sunlight, turning it into energy and releasing oxygen into the water and air. Others consumed the remains of dead organisms, breaking them down and returning their elements to circulation. Every molecule that passed through life eventually passed through them again. The balance of gases that filled the sky was not an accident, but the outcome of their patient labor. In the shadows where sunlight could not reach, other microbes performed alchemy in the dark. They fed on iron, sulfur, and nitrogen, transforming minerals into nutrients that flowed upward through the food web. Some even created their own ecosystems deep beneath the surface, drawing energy from the heat of the planet itself. These tiny beings connected every layer of Earth, from molten rock to atmosphere, in a continuous web of exchange. The nitrogen cycle, one of the quiet miracles of life, belonged almost entirely to them. Nitrogen makes up most of the air, but in its natural form it is locked away, unusable by plants or animals. Certain bacteria, living in the soil and oceans, learned how to unlock it. They fixed nitrogen into forms that living things could use, building the foundations of proteins and DNA. When organisms died, other bacteria returned that nitrogen to the air, completing the circle. Without this invisible cycle, the world's fertility would fade, and life as we know it would cease. Even today, these same processes continue, flowing silently beneath our awareness. The air we breathe, the soil we walk upon, the food that grows from the land, all are gifts from microscopic laborers that never sleep. It is strange to think of intelligence without thought, of awareness without mind. But in the collective behavior of microbes, there is a kind of wisdom. They communicate through chemistry, sending signals that coordinate growth and response. A colony can sense changes in temperature, acidity, or light, and adjust as one. When conditions shift, they share genes and knowledge between generations, teaching each other how to adapt. It is not consciousness as we understand it, but a form of shared memory written into the code of life itself. Across billions of years, this unseen network has been the heartbeat of the planet. When oxygen levels rose too high, bacteria that consumed it kept the balance. When carbon threatened to overwhelm the atmosphere, others buried it in the deep ocean and within the rocks. They have prevented catastrophe countless times, regulating Earth's systems with quiet constancy. If we could see their work in motion, it would appear like an endless slow dance of matter. Elements shifting from one form to another, atoms cycling through air, water, and stone. A single grain of sand might hold millions of them, each performing a specific task, each part of a larger pattern. To the naked eye, nothing happens. Yet, at the molecular scale, they are reshaping the planet every second. In this vast, microscopic civilization, there are no leaders, no hierarchy, no grand design, only harmony through balance. Every action, no matter how small, feeds another. Every process supports the whole. In their simplicity, they achieve what more complex life can only imitate: perfect cooperation. It is easy to overlook them, to see the forests and oceans as the main characters in Earth's story. But all those grand systems rest upon microbial foundations. They are the caretakers of balance, the silent regulators of the planet's breath and temperature. When we inhale, when we drink, when we eat, we are participating in a conversation that began with them. Even in the modern world, where humans reshape landscapes and alter climates, microbes continue their work, adjusting, stabilizing, and mending what they can. They remind us that life on Earth has always been a collaboration, one that began long before consciousness, and one that continues in every drop of water and every grain of soil. If one could listen closely enough, perhaps the planet would not sound silent at all. Beneath the wind and the waves, there would be the faint hum of unseen labor, the rhythm of cycles turning, of atoms rearranging, of life maintaining itself through the smallest of its makers. The earth still breathes because of them, and in that breath, across every ocean and mountain, the legacy of the invisible architects endures. Ancient, tireless, and essential, keeping the planet alive in ways most eyes will never see. By the time life had begun painting the oceans in blue and green, the solid bones of the planet were already shifting beneath them. The continents, slow and massive as ancient beasts, crept across the globe, drifting on the molten currents of the mantle below. They collided and separated, their edges grinding and folding, raising mountains that touched the clouds and carving basins that would one day cradle the seas. Each motion was slow beyond imagination. Entire mountain ranges rose and vanished in the span of what, to the earth, was only a few breaths. Yet these quiet collisions did more than reshape the surface. They became part of a vast and invisible balance, a planetary rhythm that would protect the world from freezing solid or burning away. This was the beginning of Earth's great climate regulator, the carbon-silicate cycle. The cycle began in the restless heat beneath the crust. Deep within the planet, volcanic activity released gases trapped since Earth's birth. Carbon dioxide was among them, a gas that, though invisible, held great power. It could trap warmth from the sun, turning it into a soft blanket around the planet. Too much of it, and the earth would swelter. Too little, and the world would freeze. Yet the earth, patient and wise in its design, found a way to regulate itself. The same forces that released carbon also drew it back in, a dance between fire and stone, air and water. When volcanoes erupted, they poured carbon dioxide into the atmosphere. Rain mixed with that gas, forming weak carbonic acid that fell gently over the continents. As it washed across the rocks, it began to dissolve minerals, carrying them toward the rivers and out to sea. There, the minerals reacted with the carbon, forming solid compounds that settled to the ocean floor. Over time, these compounds hardened into limestone and other carbon-rich rocks, locking the gas away for millions of years. It was as though the planet had built its own breathing system. Volcanoes exhaled carbon into the air. Rain, rivers, and rocks inhaled it again. The crust became both a memory and a storage, a record of every breath the earth had ever taken. This slow, geological respiration kept the climate steady across unimaginable spans of time. When the continents moved, this balance shifted. Mountains rose, increasing the surface area for weathering and drawing down more carbon. When they eroded, or when volcanic arcs grew along new coastlines, more carbon was released. The process adjusted itself naturally, responding to changes in sunlight, temperature, and tectonic rhythm. The planet had created a feedback loop, a built-in thermostat that would guard against extremes. Even the oceans played their part. Beneath their calm surfaces, microscopic organisms used carbon in their shells and skeletons. When they died, they sank, carrying carbon to the deep seafloor. There, it became buried again in sediment, completing another link in the chain of balance. Every element of this cycle, the volcano, the mountain, the raindrop, and the tiny cell, was connected. Together, they formed one of the most elegant systems in the universe, a planet that could heal and stabilize itself. To imagine this process is to picture time itself in motion. A volcanic eruption bursts with light and ash, darkening the sky for months. But in the language of the earth, it is only a brief sigh. Over millions of years, the weathering of one mountain range or the drifting of a single continent could reshape the global climate. Nothing hurried, nothing wasted. Each action met by another that restored equilibrium. This quiet balancing act is one of the reasons life could endure. Without it, the Earth might have suffered the fate of its neighbors. Mars lost its carbon too quickly, becoming a frozen desert. Venus kept too much, its air thick and choking with heat. But Earth's carbon danced in rhythm, cycling between stone and sky, maintaining a warmth that allowed oceans to stay liquid and life to grow. In the Proterozoic world, this system was still young, still finding its pace. The continents, heavy and wandering, collided to form supercontinents and broke apart again. Each collision created vast volcanic belts that fed carbon into the sky. Each separation exposed new land to the cleansing work of rain. The temperature of the planet rose and fell, but never for long. The carbon-silicate cycle held steady, adjusting like a slow pulse. Even now, that same ancient system continues. Every grain of sand that erodes from a cliff, every droplet of rain that falls on rock, every plume of gas that escapes a vent in the sea, all are part of that ancient exchange. The volcano breathes out, the earth breathes in. The balance persists. It is humbling to think that what we call climate is not just air and weather, but the living heartbeat of stone. The continents, though they move too slowly for human eyes to see, are alive in their own way, shifting to cool the planet, grinding to renew it, creating new surfaces for the endless exchange of carbon. This silent partnership between rock, water, and air has guarded life for billions of years. Through ice ages, supercontinents, and global blooms of life, it has kept the Earth within the fragile range where liquid water can flow and where life can breathe. And beneath all of it, the volcanoes continue to burn, steady and patient. Their fires rise and fade, their gases swirl through wind and water, and the balance endures. A timeless conversation between the deep earth and the open sky, between chaos and calm. The planet, as it turns, still follows that rhythm. The warmth of the sun, the coolness of rain, the drifting of continents, all in harmony, all sustained by the invisible pulse of the carbon cycle. It is Earth's way of remembering balance, of keeping its promise to life, to endure, and to remain alive. After the first blooms of multicellular life and the soft shapes of the Ediacaran seas, the Earth entered a long and patient silence. It was not a silence of stillness, but of preparation. Beneath the calm surface of the oceans, the planet was perfecting the delicate balance that would one day allow animals to awaken. The world, by now, was familiar and stable. The skies were blue, the oceans rich with nutrients, and oxygen flowed through the air in greater measure than ever before. Yet, something still held life in its quiet, restrained rhythm. The seas were filled with soft-bodied creatures that drifted, fed, and multiplied, but the energy that would one day give rise to movement, strength, and bone was still gathering slowly, molecule by molecule, across millions of years. The story of this long wait is not one of inactivity, but of patience, a kind of biological meditation. Evolution, having already learned to build complexity, now needed time to refine it, for life to grow more intricate. The planet itself had to remain calm. Oxygen, though abundant in some regions, still fluctuated. At times, the oceans would breathe deeply, rich with oxygen that sank into their depths. Then, suddenly, they would grow anoxic again, the deeper waters turning dark and still. These fluctuations shaped the rhythm of evolution, like the tide shapes the shore. Each rise of oxygen allowed life to experiment, and each fall tested its resilience. Slowly, very slowly, the balance improved. Over the course of hundreds of millions of years, the oxygen levels in the atmosphere and oceans crept upward, stabilizing into a state that life could depend on. This stability was crucial. It gave organisms the energy to build new forms, stronger bodies, more efficient metabolisms, and the beginnings of movement. Without it, complexity could not yet flourish. Meanwhile, the microscopic world remained hard at work, keeping the planet alive. Microbes continued to regulate the carbon and nitrogen cycles, ensuring the air and seas stayed balanced. Every grain of sediment that settled on the ocean floor carried with it the record of their labor, thin layers of chemical memory laid down year after year. The Earth, through these microbes, was refining its own systems, tuning its chemistry to a harmony that could sustain larger, more demanding creatures. It is easy, from the perspective of human time, to think of this era as empty. yet the world was anything but lifeless. The seas teemed with single-celled organisms and delicate multicellular colonies. There were soft mats of microbial life spread across the shallows, glowing faintly green beneath the light. There were strange forms drifting in the currents, thin ribbons of tissue, bulbous sacs, and patterned fronds, each experimenting with new ways to live. Every one of these forms was part of an unbroken chain leading toward complexity. Some refined energy storage, others communication between cells, others the structure of tissue. What seemed slow to the imagination of time was, in reality, an immense workshop, evolution sculpting, polishing, and rehearsing. The patience of the Proterozoic world gave life the time it needed to learn endurance. Unlike the sudden bursts of innovation that would come later, this was an age of refinement. Every experiment that survived became the blueprint for future creatures. The enzymes that powered photosynthesis, the genes that controlled development, the cellular machinery that built tissues, all were perfected during this long waiting period. Meanwhile, the continents continued to move. Mountains rose and eroded, releasing minerals that nourished the oceans. Volcanoes breathed warmth into the atmosphere, maintaining the planet's delicate temperature. Even the tides, pulled by the steady gravity of the moon, played their quiet part, stirring nutrients through the shallow seas. The entire Earth, in its geologic and biological processes, was working in slow collaboration to prepare the conditions for what was coming. The surface of the planet might have looked peaceful, even static, but beneath that calm, time was weaving connections. Oxygen joined with iron in the crust, with carbon in the air, and with nitrogen in the seas. These elemental dances built the chemical foundation that would allow larger, faster, more complex life to thrive. And through all this, life endured. It did not rush. It did not struggle against time. It simply continued, content in its simplicity, growing in ways that were invisible at first glance. Evolution is not always a story of leaps and revolutions. More often, it is the quiet shaping of possibility, the gathering of strength before the bloom. By the end of the Proterozoic, the world was ready, though it did not yet know it. The oceans were stable, oxygen steady, the continents alive with erosion and renewal. The microbial web that had once ruled alone now shared its dominion with creatures that could move, sense, and respond. The building blocks of the animal kingdom were all in place, waiting for the signal that would release them into abundance. If the early ages of the earth had been about survival, this one was about patience. The deep, almost sacred patience of a planet preparing for awakening. Every molecule of oxygen that lingered in the air, every slow adjustment in the chemistry of the oceans, every gentle current through shallow waters, all of it was the earth drawing a long, steady breath before its next transformation. When that breath was finally released, the oceans would come alive with movement and light, with shells and skeletons, with predators and prey. But for now, in this long and quiet interval, the world rested in balance, still, serene, and full of potential. The planet was waiting, and life, in its infinite patience, was waiting too. The long patience of the earth was beginning to pay off. After billions of years of quiet transformation, of fire and ice, of slow breathing through microbes and minerals, the planet reached a moment of balance unlike any before it. The air had been changing, molecule by molecule, rising and falling through deep cycles of abundance and scarcity. Now, at last, oxygen, the invisible thread that tied life to the world, had settled into a steady rhythm. It was not sudden. It was the result of every small act of life that had come before. Each cell that had captured sunlight, each microbe that had released a breath of oxygen, each mountain that had eroded and fed the seas. All of these tiny, Patient contributions had woven together into this moment. The oxygen in the air had climbed to near modern levels, reaching a point where it could remain stable. For the first time, the planet could truly breathe. The sky itself bore witness to the change. It deepened into a richer shade of blue as oxygen joined with sunlight to thicken the ozone layer above. That fragile film high in the atmosphere formed a shield against harmful radiation, allowing light to warm the surface without burning it. With this protection in place, the earth grew gentle. The sunlight that touched the oceans was softer, more nourishing. The air that filled the shallow seas and lapped against the land carried the promise of safety and possibility. The world had become breathable. It was not yet air in the way we know it now, still mixed with gases ancient and unfamiliar, but it was enough. For the first time in Earth's long history, oxygen flowed in quantities that could sustain larger, more active creatures. It reached the depths of the oceans, spreading life's reach into places that had once been starved of it. Complex organisms began to fill the waters, their cells equipped with the power to use this newfound abundance. Oxygen, though small and unseen, was a force of transformation. It allowed energy to flow freely within living beings, fueling movement, strength, and growth. With oxygen, life could build bigger bodies, faster metabolisms, and more intricate systems. It could move with purpose instead of drifting, react instead of waiting. Every heartbeat, every flicker of motion in the water, every whisper of nerve and muscle depended on this one element. The oceans of the late Proterozoic must have glowed with quiet vitality. Plumes of green and gold algae shimmered beneath the light, and beneath them, larger multicellular forms began to flourish. They were not yet animals in the modern sense, but their bodies hinted at what was to come. Tissues that pulsed with energy, forms that responded to their surroundings, patterns of movement that spoke of intention. The world was stirring, not in chaos, but in awakening. Oxygen also transformed the land, though it remained barren and harsh. The rocks weathered differently now, reacting with the air to form oxides and clays. The red stains of rust began to appear more often on ancient stones, a mark of the new atmosphere. Wind and rain carried the signs of oxygen's touch, etching the surface of the continents in slow, graceful strokes. The planet was learning to live with its own breath. This stability, this delicate balance, was more than chemical. It was the final key that made advanced life possible. For millions of years before, life had struggled with instability. Periods of abundance were followed by collapse, when oxygen levels would fall and the seas would turn stagnant once more. But now, through countless adjustments, the planet's systems had learned to regulate themselves. Volcanoes, oceans, and life itself had formed an unspoken agreement. The carbon cycle, the nitrogen cycle, and the flow of oxygen were now bound in a self-sustaining rhythm. The atmosphere had found its equilibrium, and in that balance, the Earth became ready for complexity to unfold. The creatures that lived in this world, the strange and soft forms of the Ediacaran, were the beneficiaries of this new stability. They could grow larger than ever before, their cells no longer suffocated by lack of oxygen. They could spread across wide regions of the ocean floor, forming networks and ecosystems that lasted for generations. Every breath they took was a part of this new atmosphere, and every movement they made sent ripples into the future. From the smallest microbe to the largest frond-like organism, each one participated in a new kind of balance, one not just of survival, but of flourishing. And yet, even as the world settled into calm, there was a quiet tension beneath the surface. The Earth was not done changing. The oxygen that had made life strong would also make it fragile. It was a double-edged gift, fuel for growth, but also a potential spark for decay and fire. It gave life freedom, but also responsibility. Still, for now, everything held. The skies remained blue, the oceans shimmered with light, and the continents rested beneath soft rain. The earth had achieved something precious and rare, a steady, breathable world. It had taken billions of years of trial and error, of frozen stillness and fiery renewal to reach this moment. From volcanic fumes to living breath, from iron seas to sapphire waters, from fragile cells to the first visible shapes of life, every chapter had led here. The air was now kind, the oceans generous, the planet warm but not cruel. The final barrier to life's expansion was gone. The world stood ready, calm and waiting for what evolution would dream next. The stage was set. The curtain of oxygen hung in the sky, clear and bright, and beneath it, the first whispers of the animal world had begun. The world had finally reached a rare kind of peace. The air was full and clear, the oceans steady and alive, the continents settled into slow and graceful motion. After billions of years of chaos, freezing, fire, and rebuilding, Earth had found a rhythm that felt almost timeless. The sky was blue and stable, the waters rich but calm, and life, though simple, filled nearly every corner of the sea. This was the closing act of the Proterozoic Eon, a quiet age of balance, the calmest chapter in Earth's long story. The oceans stretched vast and glimmering beneath a gentle sun. The atmosphere, now strong with oxygen, wrapped the planet in a breathable stillness. Rain fell softly over continents that had cooled, feeding rivers that wound their way to the coasts. The tides, guided by the moon's steady pull, moved in patient rhythm, stirring the shallows where life had found its home. Everywhere, equilibrium reigned. The chemistry of the seas no longer shifted wildly as it once had. The iron that had once stained the waters red was long gone, buried in stone deep beneath the ocean floor. Oxygen, once a rare and dangerous gas, was now woven into every breath of air, every ripple of water, every living cell. The planet was neither too hot nor too cold. It was, for the first time, comfortably alive. In this tranquil world, life flourished quietly. Mats of microbes spread across the seabed, glowing faintly in the filtered light. Soft-bodied creatures, the descendants of the Ediacaran pioneers, drifted gently in the current. Some were shaped like leaves, others like discs or ribbons. They moved slowly, feeding on the thin film of organic matter that covered the ocean floor. There were no predators yet, no chase, no fear. The living world was one of harmony and flow. It was a garden without conflict, a world of breathing patterns and steady growth. If you could stand upon the shores of that ancient time, you would see a planet at rest. The wind would move softly across the water, carrying the faint scent of minerals and salt. Beneath the waves, light would filter down in pale beams, touching shapes that shifted gently with the tide. Nothing hurried, nothing hunted. The silence of the world was not emptiness, but balance, the long-held pause between preparation and creation. Within this peace, evolution was waiting. Every creature that floated in those ancient seas carried potential hidden in its cells. The genes that controlled growth and form were becoming more intricate, more flexible. The blueprints for eyes, limbs, and shells were already written in microscopic code, though they would not yet be built. The oxygen-rich world provided the energy, the minerals, and the time. All that was missing was the spark, the change that would set those hidden plans into motion. But that spark would not come yet. The planet seemed content to rest in perfection a little longer. Continents drifted together and apart, their movement too slow to disturb the peace. Volcanoes still breathed from time to time, sending thin veils of ash into the sky, But even those eruptions felt part of the rhythm, not chaos, but balance. The Earth was practicing stability, holding steady after so much upheaval. The oceans, too, had found their balance. Circulating currents carried warmth from the equator toward the poles and returned cooler waters in kind. Nutrients flowed, feeding the smallest forms of life and supporting the great webs that grew around them. Everything was connected in a way that seemed effortless, as though the planet itself were breathing in a slow and endless meditation. It was during this time that the final pieces of life's puzzle began to align. Cells refined their internal machinery, learning to work together in new ways. Communication between them became more precise. Tissues became more specialized. Structures that had once been simple began to show hints of complexity. The potential for eyes, for muscles, for movement, all existed quietly beneath the surface, not yet awakened, but ready. Evolution was holding its breath. From the outside, nothing seemed to change. The same creatures drifted, the same tides came and went, the same quiet ruled the world. But within that stillness, something was building. Pressure, possibility, anticipation. Like the moment before dawn, when the world seems to wait for light, the planet was on the verge of transformation. This was the calm before the Cambrian, a time when life rested at the edge of explosion. In the still waters, the seeds of future worlds were already sown. The blueprints for coral reefs, forests, and flying creatures were encoded in these early forms. The chemistry of bone, the spark of motion, even the instincts of hunger and curiosity all slumbered within the molecules of the sea. The earth was ready, perfectly balanced, its systems in harmony. There was nothing violent, nothing rushed, only the quiet precision of a planet preparing itself. The oxygen was stable, the temperature mild. The continents fed the oceans with minerals. The oceans fed the air with breath. Everything was in balance, every cycle complete. And so, the world waited. The air shimmered with peace. The oceans hummed with possibility. The land, though barren, was patient, knowing that its time, too, would come. For now, the earth rested in a state of gentle perfection, as though it understood that great things should never be hurried. In that silence before the storm of innovation, life lingered in stillness, the planet's heart beating slow and steady. It was the final pause before the great symphony began. The earth remembers everything, every tide, every breath of wind, every flicker of life that ever was. All of it is written somewhere, hidden deep within its rocks. Long after oceans have vanished and mountains have been worn away, the planet keeps its quiet record. These ancient archives, locked in minerals and layers of stone, tell the story of worlds no eye has seen. For the Proterozoic world, there are no bones, no shells, no forests left behind. Its inhabitants were soft and fleeting, their forms lost to time. Yet the stones beneath our feet still whisper what they can. They speak in color and texture, in chemistry and grain. They hold within them the history of a planet becoming itself. If we could walk across the ancient surface of the earth as it once was, we would see none of what we know today, but we would stand on the foundations of it all. The rocks from that time carry the fingerprints of transformation. In some places, geologists find layers of deep red and silver-gray ironstone called banded iron formations. These layers, alternating between rich iron and pale silica, are among the oldest and most revealing records of life's impact on the planet. They were born in the ancient oceans, when iron dissolved in the water met the oxygen released by photosynthetic microbes. As oxygen combined with the iron, it rusted, falling to the sea floor in waves of sediment, like the breath of the planet captured in stone. Each layer tells of a pulse in the rhythm of early Earth. moments when oxygen surged, then fell away again, a pattern that lasted for hundreds of millions of years. These quiet bands, now buried deep in continents across the world, are the memory of the great oxygenation, preserved molecule by molecule. Elsewhere, the stones tell different stories. In the oldest reefs of Western Australia and South Africa, pale, knotted structures rise from ancient seabeds in the stromatolites. They are built by layers of microbial life, thin films of cyanobacteria that trapped and bound sediment over eons. Their shapes, still standing in the rock, resemble low domes or rippling mounds, like frozen waves of time. Each one is a monument to persistence. These microbial reefs thrived in the shallows, breathing light and carbon dioxide, releasing oxygen into the water around them. Their slow labor built the foundation of Earth's breathable air, and their patterns can still be seen in a few quiet corners of the world today. In Shark Bay, in Western Australia, and a handful of other ancient lagoons. To look at them now is to glimpse the living architecture of the Proterozoic world. Then there are the rocks that speak of cold, the glacial deposits. Found in places that were once tropical, these layers hold the scars of ice that reached nearly to the equator. Smooth boulders, scratched and polished by glaciers long gone, rest within layers of sediment. Dropstones, pebbles, carried by floating ice and released into mud when it melted, our body scattered through ancient strata, marking the times when the planet froze almost completely. These deposits tell of the great snowball Earths when ice stretched from pole to pole and life survived only in scattered oases of warmth. Each rock left behind by retreating glaciers is a small echo of that global silence, a reminder that even in its harshest moments, the Earth endured. Beyond what the eye can see, scientists have learned to read the planet's subtler language, the isotopic signatures left in ancient minerals. Atoms of carbon, sulfur, and oxygen, preserved within crystals, reveal the chemistry of long-vanished oceans and atmospheres. Ratios of isotopes tell when oxygen rose, when carbon was buried, when volcanoes breathed or went still. They are the mathematical poetry of the Earth, the fine print of its ancient story. In these clues, we see not only the record of change, but the memory of balance. Each stone, each layer, each trace of isotope records a planet finding harmony. The iron formations speak of the first breath, the stromatolites, of life's persistence, the glacial deposits, of near death and renewal. Together, they form a conversation across time, between the living and the lifeless, between chemistry and biology, between the Earth that was and the one that is now. What makes these clues remarkable is not only that they survived, but that we can read them at all. The rocks of the Proterozoic are unimaginably old, reshaped by pressure, heat, and time. Yet still, faint patterns remain, enough for us to reconstruct a world that ended more than 2 billion years ago. When geologists split open these ancient stones, they are not merely studying minerals, they are listening. They are hearing the breath of ancient tides, the pulse of volcanoes, the quiet rhythm of oxygen rising through the seas. They are tracing the first steps of life through the silence of deep time. Every fossilized ripple, every streak of rust-red iron, every glacial scar carries a piece of that distant Earth, a reminder that the world we walk on today is built from stories written in stone. And though the creatures of that age have vanished without a trace, their legacy remains. It lives in the color of the sky, the chemistry of the air, and the memory of the rocks beneath us. The Proterozoic may be silent, but the Earth remembers. Its stones are its memory, and through them, the ancient world still speaks, softly, patiently, across the long ages of time. The Proterozoic was not a single moment, but a breath that lasted more than 2 billion years, a quiet inhale and exhale in the rhythm of Earth's becoming. It was the eon of patience, of building foundations and testing balance. And as it neared its end, the planet did not erupt in chaos or sudden transformation. Instead, it changed the way night yields to dawn, gradually, softly, almost imperceptibly. By the time the Proterozoic began to fade, the Earth was no longer a place of silence and shadow. The oceans had cleared, oxygen flowed freely through air and water, and continents stood firm beneath a pale blue sky. The planet, once harsh and alien, now looked almost familiar. If you could have stood upon one of those ancient shores, the air would have tasted clean and light. The waves would have carried the scent of minerals and the faint trace of life. Beneath the surface, the water would have shimmered with motion, not yet the busy bustle of the modern sea, but a slow ballet of soft-bodied creatures drifting, feeding, and growing. The Ediacaran world, the last chapter of the Proterozoic, was full of calm purpose. Vast mats of microbial life covered the seafloor, weaving oxygen into the water. Larger multicellular beings, strange and elegant, moved gently through the currents. Dickinsonia, broad and leaf-like, rested upon the sediment, absorbing nutrients through its underside. Sprigina, with its faint segmented body, inched along like the early echo of movement to come. Frond-like creatures swayed upright from the ocean floor, rooted but alive, drawing sustenance from the surrounding water like silent underwater gardens. There were no eyes yet, no jaws, no bones. The seas were filled with softness, shapes without edges, life still feeling its way forward. The predators of the future had not yet been imagined. For now, existence flowed slowly and without fear. Yet even in this peace, change was stirring in the deep. The oxygen that had stabilized the world now reached deeper into the seas than ever before. It awakened regions that had once been stagnant and lifeless, inviting complexity to take hold. Cells that had once lived alone began communicating more efficiently, dividing tasks among themselves, forming tissues that could react and respond. Muscles began to twitch, nerves to sense, bodies to move with direction. Evolution was no longer wandering, it was learning to build. The Earth, too, continued to reshape itself. The supercontinent Rodinia had broken apart, its fragments drifting across the planet's surface. Oceans expanded between them, rich with nutrients and light. The circulation of water and air grew stronger, mixing elements across the globe. The climate, though sometimes erratic, held within it the balance that made innovation possible. Everything, from the chemistry of the seas to the geometry of the continents, seemed to align in preparation. The Proterozoic was ending, but not in decay. It was ending in perfection. Over its immense span, the world had transformed from a hostile sphere of rock and gas into a breathing, balanced planet. The first glimmers of cooperation between cells, the slow construction of oxygen's delicate dance, the stabilizing of temperature and climate, all had been achieved here. It was not a quiet story because nothing happened, but because everything important was happening beneath the surface, unseen. The end of the Proterozoic was not a closing curtain, but a pause, the stillness between breaths. Soon, the Earth would see eyes open for the first time, muscles would flex, mouths would form, creatures would begin to chase and flee, to sense and think. The calm would give way to motion, the soft shapes of the Ediacaran would vanish, replaced by armored forms and complex designs. The Cambrian would bring the age of sight and skeletons, of predators and ecosystems that mirrored the energy of life as we know it. But all of that was still in the future. For now, the Proterozoic ended as it had lived, with patience and grace. If you could watch the transition unfold, you might not notice it at all. There was no single day when the old world ended and the new one began. The change was written in slow layers of sediment, in the faint increase of fossils, in the chemistry of the ocean, and the pulse of the air. The rocks that record this moment do not tell a story of destruction, but of awakening. They show traces of calcium shells just beginning to form. They preserve the last of the soft-bodied creatures and the first signs of skeletons. They capture the balance between what was and what would be, the world holding its breath before exhaling into life's great expansion. The Proterozoic's legacy was not the creatures it left behind, but the stage it built. It gave Earth its oxygen, its continents, its climate, and its capacity for complexity. It transformed chaos into order, chance into possibility. Every forest, every animal, every human breath traces its ancestry to that long, patient age. And so, after 2 billion years of quiet preparation, the world stood ready. The oceans gleamed with promise, the air shimmered with light, the continents waited beneath warm rains. The longest eon had ended, and the story of life, the one that would fill the world with color, sound, and motion, was about to begin. In that still moment, between the last ripple of the Proterozoic and the first spark of the Cambrian, the earth rested, balanced, whole, and alive. It turned slowly beneath a golden sun, ready to dream again. The story of the Proterozoic is not only one of chemistry and evolution, it is a story of patience, of how life, air, and stone learn to coexist in balance over unimaginable spans of time. If the earlier eons were the planet's childhood, full of fire and instability, then the Proterozoic was its long adolescence, a slow, steady, maturing into stability. From this ancient world, we can read more than the history of what happened. We can read a lesson in how to live. The Earth did not rush toward complexity. It took billions of years to prepare the conditions that would one day make forests and animals possible. Every rise in oxygen was followed by a fall. Every new burst of life was tested by collapse. The world cycled through hardship and renewal until balance became its nature. Through this rhythm, the planet built the atmosphere, oceans, and continents we now depend on. There is wisdom in that slowness. When we look back at the Proterozoic, we see a planet that learned the value of waiting. The oxygen that fills our lungs today came from countless generations of unseen organisms, tiny, fragile cells that never knew the importance of what they were doing. They worked without intention, yet through their quiet persistence, they changed the fate of every future creature. The air we breathe is a gift from patience itself. Stability, too, is something the Earth learned the hard way. The cycles of ice and fire, oxygen and stone, were not mistakes but lessons. Each imbalance forced a correction. When the world froze under sheets of ice, volcanoes breathed carbon dioxide until warmth returned. When life filled the air with oxygen, the planet found ways to use it, binding it to minerals, forming ozone to shield the sky. The Earth was not a perfect system from the start. It became one through trial and resilience. In that resilience lies a quiet beauty. The planet is not delicate, yet it is not invincible either. It survives by adapting, by finding equilibrium even after catastrophe. The rocks that formed during the Proterozoic record these recoveries. The rusted layers of ancient iron, the fossils of microbial reefs, the glacial scars carved by ice and time. Each one is a memory of how the Earth found balance again after near death. It is humbling to think that the world we know, so full of motion and life, emerged not from chaos, but from calm repetition. The Proterozoic shows that change need not be fast to be powerful. The transformations that matter most often happen slowly, quietly, beneath the surface. In the stillness of that age, the planet taught itself to breathe evenly. Its atmosphere stabilized, its oceans circulated, its continents drifted just enough to keep nutrients flowing. Life responded with equal steadiness. Microbes learned cooperation, cells merged and shared energy. Complexity was born not through competition, but through union, through the act of working together. That lesson endures. Modern life, in all its speed and urgency, often forgets what the earth once knew so well, that survival depends on balance, not excess. The same cycles that governed the Proterozoic still shape our world today. Carbon moves between ocean and air. Oxygen flows through living bodies and returns to the atmosphere. The balance that sustains us is the same one that stabilized billions of years ago. When we disrupt it, the planet does not rage. It simply begins the slow process of correction, just as it always has. But unlike the Proterozoic, we are now here to witness it and to choose whether we move with it or against it. In studying that ancient eon, scientists uncover more than data. They uncover perspective. The rocks that hold the memory of the Proterozoic remind us how long true balance takes to form and how fragile it can be once achieved. They show that life thrives best not in extremes, but in the spaces between them, where temperature, chemistry, and time meet in harmony. The patience of the earth shaped everything that came after. From its slow experiments in oxygen and light, the planet learned how to cradle life gently enough for it to grow. The creatures of the Proterozoic, the stromatolite builders, the oxygen makers, the early multicellular pioneers, were the architects of that stability. Their work was invisible, but their legacy is everywhere. Every breath, every leaf, every movement of life carries the memory of their endurance. In that way, the Proterozoic is still with us. It lives in the calmness of the oceans, in the balance of seasons, in the rhythm of day and night. It teaches that progress is not always a race, that sometimes the greatest transformations are the ones that unfold too slowly to see. If we could listen to the earth speak from that age, it might say that strength comes from persistence and harmony from humility. It might remind us that everything enduring, atmosphere, life, and peace, begins with patience. And so, the longest eon leaves us not only with evidence of what once was, but with a quiet philosophy. To live as the earth once did is to embrace cycles rather than fight them, to find beauty in stability, and to trust in the slow wisdom of time. For the world that emerged from the Proterozoic was not hurried, nor loud, nor reckless. It was steady, deliberate, and full of grace. And in that ancient calm, the earth discovered the art of balance, a lesson it still offers to those who listen. By the time the Proterozoic eon had ended, the earth had done something extraordinary. It had learned how to live. For more than 2 billion years, the planet had been experimenting, not with intention, but through rhythm and patience. From its molten beginnings, it had cooled and stabilized. From chemistry, it had found biology. From chaos, it had built balance. The story of life did not begin with complexity or speed or brilliance. It began with endurance. It began with the quiet determination of a planet learning its own nature. At first, life was only chemistry that refused to stop. Simple molecules found patterns that worked, ways to persist and replicate, to draw energy from the world around them. These early reactions were fragile, yet relentless. Over time, they began to build systems, tiny membranes to protect themselves, tiny engines to feed and grow. Every failure became a lesson. Every collapse taught stability. Slowly, through countless experiments, life became less about surviving accidents and more about shaping its own future. The Proterozoic was the age of this learning. the planet discovered how to regulate itself. Volcanoes and weather began to work in rhythm, balancing gases in the sky. Continents drifted in cycles that mixed nutrients across oceans. Microbes wove invisible threads between air, water, and stone, cycling carbon, sulfur, and nitrogen in endless motion. The world was no longer just a surface where life existed. It had become a single, breathing system, a planet alive in all its parts. From this quiet collaboration between life and earth, everything else would follow. The oxygen that had once been poison became breath. The cells that had once lived alone began joining forces, creating communities that could do together what no single cell could do alone. It was in this cooperation that the first spark of complexity began to shine. Inside the oceans, new partnerships were forming. Some cells merged, becoming one, each sharing its strength with the other. One provided shelter, the other provided energy. From this unlikely union came the ancestors of every complex creature to ever exist. Within them were mitochondria, tiny, ancient descendants of free-living bacteria, still working today in every human, every animal, every plant. The energy that flows through your body right now began in the chemistry of the Proterozoic seas. The Earth had not only stabilized itself, it had invented collaboration. As ages passed, this spirit of connection deepened. Organisms began to divide their labor. Some cells became the muscles that moved, others became the nerves that sensed. Some specialized in gathering sunlight, others in breaking down nutrients or carrying information. From cooperation came structure, from structure came form, from form came possibility. Every shape of life that followed, every leaf, every fin, every feather, was an echo of this early lesson that survival is not only about strength, but about harmony. The Proterozoic taught the planet that thriving meant sharing energy, not hoarding it. Even catastrophe became a teacher. When the Earth froze nearly solid, life found warmth in deep oceans and volcanic vents. When oxygen rose and choked the old forms, new ones adapted and endured. Every disaster was folded into the planet's memory, every near extinction a rehearsal for resilience. The world did not simply withstand change, and it learned from it. That is what it means for a planet to live. When we look at the Earth today, at its forests breathing with oxygen, at rivers carrying minerals from mountains to sea, at animals that walk, fly, and dream, we are looking at a world that carries the memory of those ancient experiments. Every living thing is a continuation of the Proterozoic's long patience. The human body, the coral reef, the cloud above a rainforest, all are patterns first drawn in the chemistry of that forgotten time. The DNA in your cells is not just your own story. It is the record of an entire planet learning how to organize energy into awareness. Within it are traces of the first cells that joined together, of the first oceans that rusted red, of the first breath of oxygen that cleared the skies. You are built from the same molecules that once drifted through those ancient seas, learning how to live in the only way the Earth knew, slowly, patiently, beautifully. There is a gentle truth in this history. The Earth was never a passive stage for life. It was a participant. The rocks, the air, the oceans, all shaped what life could become, just as life shaped them in return. The balance between destruction and renewal, between heat and cold, between simplicity and complexity is not random. It is the pulse of a living planet. From chemistry, it learned structure. From catastrophe, it learned balance. From stillness, it learned movement. And from connection, it learned consciousness. The Proterozoic may seem distant, yet its lessons are written in everything that exists today. Every ecosystem, every breath, every pattern of weather still follows the rhythms that began then. The cooperation between cell and cell, between organism and planet, continues. Only now we are aware enough to see it. To live is not only to survive, but to participate in the balance that makes survival possible. The Earth learned that long before we arrived. It learned that harmony requires time, and that even the smallest beings can change the fate of worlds. And so, from the quiet depths of the Proterozoic, the planet emerged not just as a place where life existed, but as life itself, whole, self-regulating, creative, and aware. It was no longer a world enduring its conditions. It had become a world shaping its destiny. From the smallest spark of chemistry to the first stirrings of consciousness, the earth had found its rhythm, the rhythm of living, breathing, and evolving. The planet had learned, at last, how to thrive. For 2 billion years, the world whispered before it spoke. The Proterozoic was an age without noise, without spectacle, without rush. Yet, it was during that long silence that everything we know was born. It was not an era of monsters or mountains, but of patience, of invisible transformations unfolding beneath still seas and quiet skies. Every breath you take, every tree, every heartbeat is an echo of that age. The world then was slow and deliberate. Oceans shimmered with microscopic life that could not yet dream of eyes or motion. Continents drifted with the calm certainty of time itself. Volcanoes breathed in rhythm with the deep mantle, sending minerals into the sea, feeding the unseen architects that worked in the dark. There was no applause, no moment of brilliance, only persistence, the kind that shapes eternity. Life in the Proterozoic did not conquer its world. It learned to coexist with it. Every cell that survived did so by adapting, by finding harmony with the forces that could destroy it. Through these fragile beginnings, the planet discovered balance between oxygen and carbon, between ice and warmth, between creation and collapse. This balance is what makes Earth unique. Other worlds may burn brighter or swirl with storms, but few have achieved such quiet endurance. The Proterozoic gave Earth not just life, but the wisdom to sustain it. When oxygen first filled the air, it was not a gentle arrival, it was a revolution disguised as breath. It poisoned as much as it nourished, ending one world to build another. Yet, through that quiet destruction came renewal. The oceans turned from red to blue, the sky cleared, the planet learned to protect itself beneath a shield of ozone. From that fragile stability, everything else began to bloom. Even the stillness of those long ages carried purpose. While life remained simple, it was building the tools of complexity, experimenting with energy, memory, and cooperation. Every multicellular form that would later swim or crawl or walk was hidden inside those experiments, waiting for its moment. There is something profoundly human in that patience, in the idea that greatness begins in obscurity. The Proterozoic reminds us that time does not hurry what is sacred. It allows things to grow in their own rhythm, guided by quiet persistence rather than force. Imagine the Earth at the end of that long eon. The oceans no longer suffocated in iron. The continents stood steady beneath a breathable sky. The first faint creatures had begun to move with purpose, tracing patterns across the sea floor. The air was cool, the light gentle. Nothing in that moment would have looked remarkable, yet everything was about to change. The revolution had already happened. It simply did not look like one. We often think of progress as loud, as fire, motion, and explosion. But the Earth's greatest transformation was silent. It happened in the chemistry of cells and the slow building of atmosphere. It was not a single event, but a continuous unfolding, a million small changes accumulating into wonder. Even now, the same principles guide us. The oxygen we breathe is still replenished by microscopic organisms, descendants of those first ancient builders. The balance of the planet still depends on invisible processes that never sleep. Beneath every forest, within every coral reef, the quiet machinery of the Proterozoic continues, cycling elements, shaping climates, nurturing life. In that sense, the Proterozoic never truly ended. Its lessons are alive in every act of balance, every gentle rhythm that keeps the earth in motion. It reminds us that life is not a battle to be won, but a harmony to be maintained, that the smallest actions, repeated faithfully, can change the course of worlds. When we look back across the immensity of time, it is easy to overlook this age, to focus instead on the Cambrian explosion, the rise of dinosaurs, or the march of humans. But without the Proterozoic, none of those moments could have happened. It was the foundation, the slow heartbeat, that made all others possible. It taught the planet how to sustain, how to adapt, how to live. The rocks still remember it. Within banded iron, within ancient reefs and frozen sediments, the story is written not as a record of chaos, but of calm. The Proterozoic did not demand attention, it simply endured. It transformed the uninhabitable into the hospitable, the barren into the fertile, the impossible into the inevitable. And in that endurance, it left us a quiet inheritance, the gift of breath, of balance, of being. So when you breathe, remember that your lungs are part of a cycle that began billions of years ago, when invisible life first learned to shape the air. When you stand beneath the blue sky, remember that its color was painted by ancient oxygen. When you listen to the wind, you are hearing the continuation of that long, slow revolution that once filled the planet with silence and then, gently, with life. The Proterozoic was not an age of noise or conquest. It was an age of becoming, a long preparation for everything that would follow. For 2 billion years, the world whispered before it spoke. The Proterozoic wasn't loud, but it changed everything. Every breath you take is the echo of that age. The most important age in Earth's history wasn't the one that shouted the loudest, but the one that taught life how to begin.